So good morning, everybody. Welcome to the third part of the Difference in Differences course with Clément de Chaisemartin here in person in LISER. I guess we don't need, again, to remind everything, but know that the class is recorded. So if you don't want to be recorded, don't ask questions, but I hope you will ask questions. I guess I can directly give the floor to Clément. So we start right on time this time. Thank you.
Okay, I thought it was. Is it better now?
Yes, you can.
Yeah, it's good. Okay. So this quantity here is supposed to estimate the expectation of the outcome without treatment of the treatment group at period 2. So unfortunately, this estimator here could fail to satisfy a desirable property. So which property is it that this estimator could fail to satisfy?
No.
In the specific context where we're interested in a binary outcome variable, like, you know, whether someone is employed or not. Yeah, exactly. This thing here could be outside of the 0-1 interval. So for instance, think of a case where at period 0, the average outcome in the treatment group is 0.8. And from period 1 to 2, the average outcome in the control group goes from 0.4 to 0.7. Then, according to the parallel trends assumption, the average outcome in the treatment group would also have increased by 0.3 between period 1 and 2, but that would lead us to a predicted outcome in period 2 of 1.1, which is impossible. Okay? So, as a solution to this problem, Blundell et al. And Wooldridge, they've proposed to replace this the classical parallel trends assumption by the following condition here. Okay, we assume that L-1 of the expected outcome without treatment at period 2 in the treatment group minus L-1 of the expected outcome without treatment in the treatment group at period 1 is the same as the same thing, but in the control group. Okay, so essentially we assume parallel trends, but not for the average outcome without treatment, but for a transform of the average outcome without treatment, where L is a strictly increasing function that takes values in the 0-1 interval. So for L equal to the identity function, this equation 3.33 is actually equivalent to the standard parallel trends assumption. Okay. So now we're going to try to show that the average outcome without treatment in the treatment group at period 2 is identified under this condition. So to show that, we start from what we want to identify. And then we just say that this quantity is just L of L-1 of the same quantity. And then to go from here to here, we are just adding and subtracting this term here, okay, which is L-1 of the average outcome without treatment in the treatment group at period 1. And now here we have an evolution of L-1 of the expected outcome without treatment between period 1 and period 2, okay? So now how do we go from here to here? Yeah, exactly, by our parallel trends assumption on L-1 of the expected outcome without treatment. Now we can replace this evolution by the same evolution, but in the control group. Notice that the superscript here is moving from 1 to 0. We are looking at the treatment and now at the control group. And now all of those untreated outcomes are observed, because here we are looking at the treatment group at period 1, so their untreated outcome is just their actual outcome. Here we are looking at the control group at period 2, so their untreated outcome is just their actual outcome, and same thing here. And so therefore, we've shown that this unobserved counterfactual outcome is actually identified by relating it to random variables that are all observed. So now that we've shown identification of the average outcome without treatment, we can move on to estimation. So typically for estimation, we just replace expectation by sample averages. So if we want to estimate this expectation, we are just going to follow this formula, but we forget about the expectations, okay? And that will give us, this thing here will give us an estimator of the average outcome without treatment at period 2 in the treatment group. And then to estimate the ATT, we just compare the actual outcome in the treatment group at period 2, which is under the counterfactual where they are actually treated, to what would have happened to them without treatment. Now, it turns out that this estimator here is numerically equivalent to that estimator here, where those alpha at 0, alpha at 1, alpha at 2, alpha at 3 are the coefficient that are the maximum likelihood estimators that you get from a binary choice model that assumes that the probability that YGT is equal to 1 is L of alpha 0 plus alpha 1 times the treatment dummy plus alpha 2 times the period 2 dummy and alpha 3 times the interaction of the two dummies. So if the L function that you choose is, for instance, the logistic CDF, then what this means is that to estimate the ATT, you just need to run a logit regression of your outcome on an intercept, a treatment group dummy, a period 2 dummy, the interaction of the two dummies. Then you estimate the coefficients in the model, and then you estimate the ATT as essentially the predicted success rate under treatment, according to the logit model, minus the predicted success rate for the treatment group at period 2 if they had been untreated. And the big advantage of expressing our ATT estimator in this way rather than in that way is that here our ATT estimator is only a function of coefficients from logit or probit regression, such that if you want to if you want to estimate the variance of that estimator, you can do that using pre-canned post-estimation logit or probit routines that are pre-canned in Stata or in R. Okay, and this type of diff-in-diff logit or probit regressions, they were first considered by Puani 2012. So now, with a binary outcome variable, we think there is really no reason to not use this type of probit or logit diff-in-diff estimator, because they are equal, just almost as simple to compute to the marginal difference that running a logit takes or a probit takes a very small amount, just a little bit more time on even modern computers than running an OLS regression. But computing this type of probit or logit Diff-in-diff estimators is almost as fast as running a two-way fixed effects regression. And drawing inference, estimating the variance of the estimator is also very straightforward. So there is really no reason when you have a binary outcome variable to not use this type of estimator, because by doing so, you circumvent the issue that we just discussed, that the standard parallel trends assumption that underlies the linear estimator can lead to weird predictions, to nonsensical predictions when the outcome is binary. So,
Clément, I have a question.
Yeah.
Don't we have the problem of nonlinear models when we have too many fixed effects?
But here we don't have too many fixed effects.
We don't have too many.
That's a very good point, and we'll get back to that issue when we talk about binary and staggered designs. Yeah. But really, okay. So let me just elaborate a little bit on that. So in the linear case, we actually saw that running a two-way fixed effects regression where you have one fixed effect for each group, or running a two-way fixed effects regression where you have just one fixed effect for the treated groups, we saw that the two things actually give you numerically equivalent treatment coefficients. Here, it's not a coincidence if for the nonlinear model, I'm actually not putting in all the group fixed effects, and instead I just have one fixed effect for the treated groups, because now in the context of nonlinear models, we would not have a numerical equivalence between the two, and actually putting in too many fixed effects in a nonlinear model can give rise to what's called an incidental parameter problem, whereby the coefficients, the maximum likelihood estimators are not consistent anymore when the number of time periods that we use for the estimation is not very large, okay, which is typically the case in Diff-in-diff applications. So here we are avoiding this issue because we have only this fixed effect here rather than having one fixed effect for each group. Okay, so 0-1 dependent variables are not the only type of limited dependent variables that we encounter in applied economics research. Another very frequent case of limited dependent variables are non-negative dependent variables. Okay, variables that cannot be negative, like trade flows between two countries. And in that case as well, we also have the issue that even though it's probably a little bit less likely to arise, we could theoretically at least also have the issue that the linear parallel trends assumption gives you nonsensical prediction. It could predict a negative counterfactual trade flow between two countries. And so to avoid that, you can use a Poisson regression of YGT on, again, an intercept, the treatment group dummy, the period 2 dummy, and the interaction of the two dummies to estimate the average treatment effect on the treated. And Wooldridge shows that this estimator relies on a parallel trend assumption on a transform of the outcome without treatment. And here, in the case of Poisson regression, the transform has actually a very intuitive interpretation because the transform is actually just the logarithm function. Okay, so this type of Poisson regression relies on a parallel trend assumption on the log of the average outcome without treatment. Okay, so now we are going to skip quite a bit of material, but I'm just going to highlight it so you know where to look if you're interested in those topics. So a related topic is the issue of sensitivity to functional form, the fact that Diff-in-diff models can give you different results when you use y or log of y as your outcome. This topic is discussed here. And another related topic is the estimation of quantile treatment effects. Namely, instead of estimating the effect of the treatment on the average of the outcome, maybe we're interested in how the treatment affects the median of the outcome or the top decile or the bottom decile of the outcome. And so we discuss the various estimators of quantile treatment effects in Diff-in-diff models that are available in this section. Okay, and finally, I'm also going to skip some further topics. So here we discussed imbalance panels. So I've been assuming that the GT level panel is balanced, which oftentimes is not the case. And so here we discuss what to do in those cases. And here we discuss the issue of weighting. Because oftentimes researchers want to weight their model by, let's say, the population of cell GT. You know, if you're running an analysis using US state level data, maybe you don't want to give the same weight to California and to Vermont. And the last topic that's being discussed here is how we can account for and estimate spillover effects when we fear that some of our control groups, some of our control locations, let's say, they don't receive the treatment, but because they are close by to locations that are treated, they might still be affected by the treatment. There is, so most of the Diff-in-diff literature is ruling out spillover effects, like I said in the very beginning. There are just a handful of papers that try to relax this assumption. And what those papers have been doing so far is not very different from what applied researchers are already doing when they fear that they might be spillovers, namely assuming that spillovers can only occur within a certain radius of treated units. Let's say that, you know, a control county can only be affected by the treatment if it's within 100 kilometers of a treated county. And then you just redo your Diff-in-diff analysis where comparing treated groups to control groups that are more than 100 kilometers away from from any treated county. And there is this paper there are these two papers by Clark and Butts that, so the paper by Clark shows how your Diff-in-diff can be biased if you don't do that, if you ignore the fact that actually some of your controls are treated. And Butts is the paper that tries to formalize this idea of excluding the controls that are too close to treated location. Okay, so now the next step. So we conducted this survey where so first we looked at the 100 most cited papers that have been published by the American Economic Review from 2015 to 19. And we found 26 that estimate at least one two-way fixed effect regression. So it's just to give you a sense of how common, how prevalent this type of research design is. It's probably we've not done the same exercise for RCTs, RDs, IVs, etc. But it's hard to envision how, you know, like just mathematically, actually, at the end, it would sum to more than 100. But it's hard to, it's not very plausible that you would find more than 26 RCTs, let's say, in those 100 papers. Now, so the first takeaway is that those type of estimation techniques are all over the place. The second thing is that of those 26 papers, there are actually only two that have an absorbing and binary treatment with no variation in treatment timing. So that shows that what I'm calling the classical Diff-in-diff design is really more the exception than the norm in terms of the research designs that applied researchers face typically. And so what we will do in the next chapters is to try to consider more general designs to relax the assumption that the treatment is binary, absorbing, and that there is no variation in treatment timing. But before we do that, we are going to first spend a little bit of time on potential relaxations of the parallel trends assumption. Okay, because the estimators we've seen so far assume parallel trends, and maybe that assumption is not always plausible. So we're going to discuss the main relaxations of that assumption. Yes?
Yes, Clément. Sorry, just to interrupt you. Just before you go further, it's fine. It's fine. I'm just coming back one sec to the linear versus nonlinear models.
Yeah.
Because we know that usually in practice with really standard regressions, when we use LPM or Probit, we get more or less the same results. And so since you have replicated, I'm assuming you are replicating this paper, or you have looked at this paper, the 26 2 fixed effect in the AER. I was just wondering whether does it make a change in practice?
Okay, so
based on the paper that already exists.
So I've not done this exercise.
Okay.
But so there is no reason not to do it, not to use these Probit or logit estimators. But it is true that in practice, doing so rarely makes a big difference. And here it's not, it's anecdotal. It's not like based on the meta-analysis of 30 papers, but anecdotally, yeah, it does not lead to a big difference. And in fact, so this in the context of this Moser and Vuena application that we've been working on, the data, the outcome variable is a count variable, it's patents, and so I've seen, I don't even know if it's in a paper. I've seen on social media on Blue Sky that Wooldridge has actually replicated this paper using a Poisson regression instead of a linear regression, and indeed the results look essentially identical. So. Yeah.
Okay. So then, in that case, when using this binary outcome variable, if the potential outcome the predicted potential outcome is within the range of 0 and 1, you would say it's fine to use just linear.
Yeah, probably in that case. The strong argument in favor of not using this nonlinear model, of not using the linear model, does not apply anymore. Yes, I agree. Yeah. And like you see, and actually there as well, it's related to sensitivity to functional form. In my numerical example that I gave at the very beginning, where I had like the treatment group at 0.8 and the control group going from 0.4 to 0.7. Predictions outside of the 0-1 interval can only arise when the levels of the outcome of the treated and the controlled are very different at period 1. Okay, because if they are the same, like if in my example, both were at 0.4 in the first period, then any outcome evolution of the control group can only yield a predicted outcome for the treatment group that's within the 0-1 interval. Okay, so this type of concerns with the linear parallel trends assumption or with sensitivity to functional form are much more likely to arise when the levels of the outcome are very different in the pre-period in the treatment and the control group. So that's something that you can easily check And if it seems that the levels of the outcome are not that different, then maybe you can forget about all these issues. But if the levels of the outcome are very different at period 1 in the treatment and in the control group, then maybe you want to keep those issues in mind and at least run a probit or check for sensitivity to functional form as a robustness check. Okay, so so we're going to discuss alternatives to the parallel trend assumption. And we're going to assume that we are in a classical Diff-in-diff design. We're going to rule out dynamic effects. It's just to simplify the notation. It's not substantively important. And now we are going to first, so the main strategy to relax parallel trends. So there are, I would say, 3 main strategies available in the literature. The first one is to add control variables, to add covariates to the model. And that's the one we're going to be reviewing together. Then the second one is to move from a Diff-in-diff model to a synthetic control model or to a synthetic Diff-in-diff model. That's covered in the textbook, but we will not go over that material together. And the third strategy that we will also not go over together is to replace a parallel trend assumption by the assumption that we have differential trends between the treated and the control, but the differential trends are bounded, okay, which is an approach that has been proposed by Rambachan and Roth recently. Okay, so estimators with control variables. So also to simplify, in most of this discussion, we can assume that we have only 2 time periods. So we're going to let xg denote a vector of control variables or covariates that we want to control for. And we're going to assume that xg is non-stochastic or conditioned upon. Okay, so in all this section, we're going to treat xg as if it was, as if they were constant. And so the main benefit of introducing controls into the estimation is that this allows us to relax our parallel trend assumption. We can replace our assumption PT by assumption CPT, the conditional parallel trend assumption, which requires that there exists some function such that the expected outcome evolution without treatment is equal to m of xj. So I would like you to try to interpret this CPT assumption. Yeah.
Yeah, I mean, does it basically bring us to sort of sort of parallel trend of the residuals? Basically, is that where this is taking us, more or less?
No, not exactly. So it's imposing parallel trends for some groups, but allowing for differential trends for other groups. So which groups are going to be required to be on parallel trends under this assumption, and which are the groups that are allowed to be on differential trends?
Then we'll assume that the groups are the same bounds. Variable with not and then variation have a single variable with action.
Yeah. So here, what this is saying is that the counterfactual trends are a function of the covariates. Okay, so that means that if you have 2 groups G and G prime that have the same covariates, so in your example, if 2 individuals have the same gender, then they are required to be on parallel trends, while 2 individuals G and G prime with different values of the covariates, with let's say different gender in the example, are allowed to be on differential trends. Okay, so that's why we say it's a conditional parallel trends assumption, because we say that conditional on two units having the same covariates, they have to be on parallel trends. But if those two groups have different values of the covariates, they can be on differential trends. Okay, and now it's going to be convenient to assume that sometimes it's going to be convenient to make a functional form assumption for this function m, and namely assuming that the m function is linear. So the conditional parallel trends assumption with a linear functional form, which we're going to call assumption LPT, linear parallel trend, requires that that the counterfactual outcome evolution without treatment is an intercept gamma 2 plus x prime g times theta for a vector of coefficients theta. So just a few words on whether we want to make a parallel trends assumption with respect to covariates in levels or in first difference. So what I've called the control variables xj. So for now, I've not been, I've not explicited what they are. So they could be actually constructed from an original set of covariates that are actually time varying, okay, that are xgt. And a covariate, what we mean by a covariate is that it's a variable that should not be affected by the treatment. Okay, so that's a variable such that if you such that xgt of 0 is equal to xgt of 1. If you thought of two potential covariates value depending on whether you receive or do not receive the treatment, then those two potential values have to be equal. Okay, and for instance, that's going to be more plausible when the covariate is something that's determined prior to treatment. Okay. So with time varying covariates, we could control for xg1 for the baseline value of the covariate, or we could control for xg2 minus xg1. We could control for the change in the covariate, or we could actually be controlling for both. We could have that our vector of controls xg is the concatenation of the baseline levels of the covariates and the change in the covariates. So whether it's more natural to control for outcomes in levels or in changes is going to be context specific. The question you need to ask yourself is whether differential trends between groups are more likely to originate from differences in their baseline level of the covariates or from differences in the change of their covariates. So here, there's not going to be a universal answer as to which one is more plausible. The only important thing to keep in mind is that remember that to be a valid covariate, a variable has to be uninfluenced by the treatment. There should not be a treatment effect on the covariate. And this assumption seems more plausible when you control for the baseline levels of the covariate, because the only assumption you need to make for xg1 to not be affected by the treatment is that xg1 is not subject to anticipation effects, because the treatment only starts at period 2. While when you control for xg2 minus xg1, it becomes a stronger assumption to assume that this variable is not affected by the treatment, because at period 2, xg2 could respond to the treatment. Yes?
No, it's on. On weather controlling for the level of the change. In addition to what you just said, in practice, in many cases, the change depends on the level. In fact, for example, if one analyzes time series of under 5 or infant mortality, processes like that, demographic processes, mortality reduction processes are such that the speed of the process typically depends on the level. Would you say that in this case there is also kind of a fair reason to think that the level is a better way to control? Because in a sense, it implicitly controls to what should be the change if the process remains the same, let's say, but...
So, no, interesting point. So in that case, I would say there would be, I would agree with you that then controlling for the baseline level will, you know, in a sense, is going to be almost as controlling for the change, except that you will only capture the part of the change that's not caused by the treatment, that's, you know, predicted by what would have happened without treatment. So yeah, I think it's an interesting point. Okay, so first, let's look at what two-way fixed effects regression with control variables estimate. So to simplify, we are going to assume that we control for the baseline levels of the covariates, and we're ready to make our linear parallel trend assumption. Then, can you propose a very slight modification of our linear two-way fixed effect regression that we could use to estimate the ATT under this linear conditional parallel trends assumption? So under parallel trends, we just run YGT on G fixed effects, T fixed effects, and DGT. Now we don't have parallel trends anymore. We know that groups with different value of X1G, of XV1 are going to have differential trends. How should we incorporate that in our regression?
Yes, covariates.
Yeah, exactly. We're going to add the covariates. Now, XV1 is time invariant. Okay. So it's so if you just throw in XV1 in the regression, it's going to get wiped out by the group fixed effects. Yeah, exactly. So the regression we're going to be running is going to be exactly this one, where we just add one variable, or no, we just add this vector of variables. We interact the XV1 with the period 2 fixed effect to reflect the fact that units with different values of XV1 might experience differential trends. And then we also have the treatment, and because the inclusion of this variable is going to change the treatment coefficient, we now denote the treatment coefficient by beta FEX to reflect the fact that it's a two-way fixed effect estimator where we have control variables.
A question here. So, but if our fixed effects, the group fixed effects, are at a higher level, so let's say we have individual data and we control for a fixed effect at a higher level, then I guess we need to control for the X also in levels, right? Not just in trends.
Yes. Good point.
Yes.
But we're going to see that actually even doing that has some problems. So, yeah. Okay, so now we've seen that under the parallel trends assumption, beta at FE was unbiased for the ATT. So the hope would be that under our linear conditional parallel trend assumption, this beta at FEX would also be unbiased for the ATT. And unfortunately, we're going to see that this is not the case, okay? And we're going to see that this two-way fixed effect estimator can be biased if treatment effects are heterogeneous and correlated with the covariate. And to see this point, we're going to simplify and assume that actually we control for only one variable. Okay, the xv1 vector is of dimension 1. Then we let mu x1, mu x0, sigma square x1, sigma square x0 denote the average of x, the covariate among the treated groups, the average of the covariates among the control group, the variance of the covariate in the across the treated groups, and the variance of the covariates across the control groups. Then we let W1 be a weight that's going to be included between 0 and 1. That's equal to number of treated groups times the variance of the covariate in the across the treated groups, divided by the same thing plus the same thing but for the control group. Okay, so it's a bit a measure of the ratio of the variance of the covariate in the treated group relative to the variance in the total population. And finally, we let beta x have this expression here. So this thing here, you can think of it as a regression coefficient. A regression that would not be feasible, that you could not run if I were to give you a data set, but still a regression coefficient. So that would be the regression of which variable on which variable. Yeah, exactly. So that's the regression of the treatment effects on the x variable. So this coefficient is capturing essentially whether there is a correlation between the covariate and the treatment effects. So we have the following result that if we are in a classical design, we assume no anticipation and we assume that we have linear conditional parallel trends and the covariate is of dimension 1. Then the expectation of beta at Fex is equal to the ATT plus an additional term. And this additional term is this W1 weight that I just introduced times the difference between the average value of the covariate in the treatment and in the control groups multiplied by this beta x coefficient that I just introduced and that measures the correlation between the treatment effects and the covariate. And then once we have this result, we can re-express it as follows. We have that beta at Fex is unbiased for a linear combination of the TG2 effects, where the weights WG sum to 1, but could be negative. Okay. So the first equality implies that this two-way fixed effect with covariate estimator could be biased for the ATT. So it's not going to be biased when mu x1 is equal to mu x0. When the meaning that the covariate is not correlated with the treatment. That part is not very surprising. You know, by standard omitted variable bias formula, you know that if you control for a variable that's uncorrelated with your variable of interest, that's not changing the coefficient. Now, we are also going to have another case where the coefficient will not change, which is if the x variable is uncorrelated with the treatment effects, meaning that beta x is equal to 0. But if those two conditions fail, if x is correlated with the treatment variable and with the treatment effects, then beta at Fex is going to be biased for the ATT. So what's the intuition for for the fact that beta at FEX is not unbiased? Well, the intuition is that, and that's going to be an intuition that's going to be coming back again and again from now on. The intuition is that this two-way fixed effects regression is trying to do too many things at the same time, in the sense that it is trying to, at the same time, estimate the effect, the quote-unquote effect of the covariate on outcomes evolution. So this theta hat coefficient is supposed to estimate the theta that we have here, which measures the effect of the covariates on groups' untreated outcome evolutions. So the regression is trying to estimate that, how covariates affect groups' untreated outcome evolutions. And at the same time, it's trying to estimate the treatment effect. And because it's trying to do two things at the same time, we can show that this theta hat coefficient captures both the correlation between the covariate and control groups' outcome evolutions, which are untreated outcome evolutions. But because 4.1 is estimated in the full sample, not only restricting attention to control groups, this theta hat coefficient is also contaminated by the effect of the treatment. It's also capturing the effect of the treatment, and that's what leads beta at FEX to also, at the end of the day, be biased for the ATT. And you see that this contamination problem only arises if the covariate is correlated with the treatment effects. If the covariate is not correlated with the treatment effects, the fact that we estimate the effect of the covariates in the full sample, where some observations are treated and therefore their Y reflects also the effect of the treatment, then that will not contaminate theta hat. That's only if the covariates are correlated to the treatment effects that theta hat will be contaminated by that effect. Okay, and so just a few comments on the second formula. So the second formula that we have here is a decomposition of a two-way fixed effect estimator as a weighted sum of treatment effects with weights that sum to 1, but that could be negative, and which we are going to encounter again and again in the remainder of the class. And this result really directly follows from this one. You just need to note that this beta x can actually be rewritten as a weighted sum of the TG2 effects with weights summing to 0, while the ATT by definition is also a weighted sum of the TG2 effects with weights equal to 1 over G1. And that's how you can rewrite this as that here. And interestingly, so those, so in a paper with Xavier, we had considered, we had shown that generally, even outside of the special case we're considering here, where there is only one covariate, generally, two-way fixed effects regressions with an arbitrary number of covariates, they always estimate a weighted sum of effects where the weights can sum to 1, but can be negative. But what's nice in the case with only one covariate is that we can get this simpler expression here, which gives a little bit more intuition as to where the issue is coming from. And what's the issue with the negative weights? Well, the fact that the weights is some of the weights are negative could mean that you could have sign reversal phenomena where the treatment effects are all positive, but the expectation of beta at FEX is negative, meaning that even the sign of the two-way fixed effects coefficient could be wrong. Okay, but that's an issue that we're going to discuss in more details later. Okay, so because two-way fixed effects with covariates do not seem to have very desirable properties, and that's true even in classical designs with binary absorbing treatment without variation in treatment timing, then maybe we want to consider alternative estimators, and the alternative estimators we're going to be considering are going to be Diff-in-diff estimators. Yes?
A question regarding the two-way fixed effect that we just saw. I guess we can solve it by interacting the treatment dummy with the X, assuming that we are getting the heterogeneity of the treatment effect given X is correctly, no?
Yes, exactly. So assuming that treatment effect only varies with X, then that would indeed be a potential solution to the problem. Yeah. But, you know, that relies on this assumption. Yeah. Okay, so we saw that the two-way fixed effects regression with controls is biased because it's trying to do too many things at the same time, namely estimating the effect of X on the outcome evolution without treatment, and at the same time estimating the treatment effects. So instead, we're going to be proposing a two-step procedure that's actually inspired from a paper by Ekman and co-authors 1997, where in a first step, we're going to estimate this theta coefficient that appears in the LPT assumption that captures the correlation between the covariates and groups' untreated outcome evolutions. And in a second step, we will estimate the treatment effect. So I'd like to ask you, in the first step, which regression should we run to estimate this theta coefficient? So theta is measuring the correlation between groups' evolutions without treatment and the covariates. So to estimate a correlation, usually we estimate a regression. So we need to find a subsample for which we observe outcome evolutions without treatment. The control group, exactly. So we're going to take our control group, and in the control group, we're going to be regressing outcome evolutions on an intercept and the covariates. Okay, and we're going to let theta at OR, so OR because this estimation method is called outcome regression. Okay. So this estimation method to account for covariates is called outcome regression. So we let this coefficient here, and then we have theta at OR denote the coefficient on the covariates. Once you have those estimators here, can you propose an unbiased estimator of the ATT? Yeah, exactly. Up. So the Diff-in-diff estimator with covariates based on outcome regression inspired from Ekman et al. Is going to have this expression. It's going to be an average across all the treated groups of their actual outcome evolutions minus their predicted outcome evolutions if they had not been treated where the prediction is coming from a regression estimated on the control groups. Okay? And so we can show that in a classical Diff-in-diff design, under the no anticipation and linear parallel trends assumption, this estimator is unbiased for the ATT, unlike our beta hat FEX estimator that we saw earlier. So the proof follows from the fact that those coefficients, those estimated coefficients in the control group are unbiased for the true coefficients. And therefore, if we take the expectation of this estimator, well, by linearity of the expectation, we have this expression here. And then here, we are going to do our usual trick of, and we use the fact that treated groups are treated at period 1, so at period 2. So at period 2, what we observe is a y of 1. And they are untreated at period 1, so at period 1, we observe a y of 0. Then we use our usual trick of adding and subtracting the outcome without treatment at period 2. This becomes the ATT. That's just the average effect of the treatment across all the treated cells. So by definition, that's the ATT. Then how do we go from here to here? From this one here to this one here.
So that you know how the control this.
Yeah, we plug our model for the untreated outcome evolution. We've said by our linear conditional parallel trend assumption, we know that this has this functional form, okay? And I did not say that to go from here to here, we use the fact that this estimator is unbiased for that parameter. So the expectation of this is that, and similarly for here. Okay, and then you can see that those two terms are going to cancel out, and then we'll be left with the ATT. Okay, so it's a first parametric Diff-in-diff estimator with covariates. Parametric in the sense that it assumes a linear functional form for the untreated outcome evolution. Then we can use a second type of parametric Diff-in-diff estimator, which is based on propensity score reweighting, where in a first step, we're going to be regressing the treatment group indicator on some covariates. To do that, you can use a logit or you can use a probit model. Then we're going to let P hat xj denote the predicted probability that a given group would belong to the treatment group in view of its covariates. And then Abadi 2005 proposes the following estimator of the ATT, where the first term is just the outcome evolution of the treated groups. And the second term is the outcome evolution of the control groups, but where we actually reweight the control groups by this expression here. And because the function that maps x into x divided by 1 minus x is increasing on the unit interval, this means that this thing is going to be larger for control groups that have a larger P hat of xj, okay? Meaning control groups who, based on their covariates, they actually have a pretty high probability of belonging to the treatment group. So we give more weight to the outcome evolution of the control groups that actually look like treatment groups. Okay, so that's the intuition for why this estimator is going to be actually consistent here for the average treatment effect on the treated. So one practical but important point. This type of propensity score reweighting estimator, they rely on what's called the overlap condition. Namely, so here, the condition requires that the true population propensity score, P of xj, has to be bounded away from 1. Okay, P of xj has to be always lower than 1 minus epsilon for a strictly positive epsilon, meaning that there cannot be any value of the covariates for which you have only treated groups. Okay, all values of the covariates should be such that you have some treated and you also have some controls. And so when you estimate the propensity score, it might be that for some xj, P hat of xj is actually very, very close to 1. And that's going to create issues. That's going to lead to an estimator with a very large variance, because if P hat of xj is very close to 1, then this denominator is going to be very close to 0, and therefore this ratio is going to blow up. Okay. So then what people do in practice is to trim observations whose propensity score is too close to 1. And a popular rule to do that is to follow the recommendation of Crump and co-authors to trim the treatment and the control groups with a propensity score larger than 0.9. And there is actually a theoretical justification as to why the 0.9 value. The theoretical justification being that it's the one that minimizes the variance of the estimator. Okay, so now let's look at doubly robust and or non-parametric estimators with covariates. So first, we can consider, instead of using linear regression adjustment or using propensity score reweighting, we can combine the two together to get what's called a doubly robust estimator. So what's the motivation? So the motivation is that this estimator, based on outcome regression, where we regressed outcome evolutions on the covariates, is going to be inconsistent if we have conditional parallel trends, but the M function that we discussed in this assumption CPT, this M function, is actually not linear in the X's. Then if we have conditional parallel trends, but the M function is not linear, then our Diff-in-diff estimator based on regression adjustment, based on outcome regression, is going to be inconsistent because it assumes that the conditional expectation function is linear in the covariate. Similarly, our propensity score reweighting estimator has a similar issue because we use a parametric logit or probit model to model the propensity score. But if that model is misspecified, if the true propensity score does not follow a probit or a logit model, then the estimator will also be inconsistent. So as a way to alleviate these problems, Santana and Zhao, they propose to use what's called a doubly robust Diff-in-diff estimator that's going to combine outcome regression and propensity score reweighting. So one of the estimators that they propose, which I'm going to subscript by DR for doubly robust, combines, so in the outcome regression estimator, we would just have this term. In the propensity, in the propensity score reweighting estimator, we would have an estimator with the same structure, but where instead of having residualized outcomes, we would have residualized outcome evolutions. We would have the outcome evolutions themselves. And so here we combine the residualization of outcome evolutions of the outcome regression estimator with the propensity score reweighting. And what they show is that this estimator is going to be consistent for the ATT if either the M function in the conditional parallel trend assumption is indeed linear, or if the true propensity score follows the probit or the logit model that we've chosen for estimation. So we need one of the two models to be correctly specified. Either the model for the outcome is correctly specified or the model for the propensity score is correctly specified, but we do not need the two models to be correctly specified. On the other end, we need at least one of the two models to be correctly specified. So there is still an assumption, a parametric assumption we need to make. We need either the outcome evolutions to be linear in the covariates or the propensity score to follow a logit model for this W-robust estimator to be consistent. So that's why we call it a parametric W-robust estimator. So now can we do fully non-parametric estimation? Well, there is one case where doing so is going to be very straightforward, and it's a bit obvious, but it's still worth mentioning it because that's a case that arises pretty often in empirical applications. That's the case where XG, the covariates, take a small number of values relative to the sample size. Then in that case, the M function in my conditional parallel trend assumption can be fully non-parametrically estimated by regressing outcome evolutions on fixed effects for any value that XG can take, okay, in the sample of a control group. So that means that if your XG variable is of dimension 1 and takes values 1, 2, 3, 4, 5, instead of regressing YG2 minus YG1 on XG, assuming that there is a linear relationship between how YG2 minus YG1 is changing and XG on the 1, 2, 3, 4, 5 support, you just regress YG2 minus YG1 on a dummy for XG is equal to 1, a dummy for XG is equal to 2, etc. And now you're not making any functional form assumption anymore. So this type of strategy is appealing in practice, for instance, in very relevant cases where, for instance, you have a county level data set and you want to allow for state-specific trends. Okay, then if you want to do that, so meaning that you want to relax pretty substantially the parallel trends assumption by assuming no longer that all the treated and all the control counties experience the same trends, but it's only the treated and the control counties in the same state that are on parallel trends. Okay. Then to do that, you can just regress YG2 minus YG1 on state fixed effects in the sample of control counties and apply our DIDX OR estimator with that first step. Okay. And this type of strategy can also be used when you have firm level data. And instead of assuming that all the treated and the control firms experience parallel trends, you are only ready to assume that treated and control firms that belong to the same sector are on parallel trends. Then you can implement that strategy by having industry fixed effects in the residualization first step. Now, the difficult case for non-parametric estimation, to do fully non-parametric estimation, is essentially when the covariates XG take a large number of values, a number of values that's too large relative to the sample size to estimate a regression of YG2 minus YG1 with dummies for any possible value that XG can take. And that's going to be, this type of strategy is actually going to be completely impossible when some of your XG variables are continuous variables, and then for any possible value of XJ, you have actually only one group, and that's going to take that value. So in that case, if we want to estimate outcome changes as a function of the covariate MXG or the propensity score PXG completely non-parametrically, a solution could be to use non-parametric regression techniques, like, for instance, a kernel regression or a series regression. But there are lots of issues attached to those techniques. Namely, those techniques, they require choosing tuning parameters like the bandwidth in a kernel regression. And also, as soon as the dimensionality of the covariates increases, if, let's say, you do not have only one continuous covariate you want to control for, but you have 5 of them, then a well-known statistical problem called the curse of dimensionality is going to start kicking in, and you're going to get estimators with very bad finite sample properties. Now, there are very exciting developments in other branches of econometrics, which have been the recent development of doubly robust estimators, where we use machine learning methods to estimate outcome evolution without treatment and propensity scores. The issue at this stage is that these methods are just starting to be adapted to Diff-in-diff. I'm citing, the 2 examples that I know so far. And they are not implemented yet in the commonly used packages that people use for Diff-in-diff estimation with control variables. Okay, so that's a bit the state of the art for Diff-in-diff estimation with control variables. So I'm going to skip this part, but if you're interested, we talk a little bit about triple Diff-in-diff estimators. One topic that I want to spend a few minutes discussing is the topic of group-specific linear trends. So to discuss group-specific linear trends, I need to have more than 2 time periods. And actually, I'm going to assume that I have 4 time periods. And the treatment starts at the last of those 4 periods. Then the identifying assumption that rationalizes the inclusion of group-specific linear trends is the following. So the standard parallel trends assumption was assuming that groups outcome evolution without treatment was just an intercept gamma t. But now we also add a group-specific coefficient lambda g. So this assumption means that groups are allowed to be on their own group-specific linear trend lambda g. But then from period t-1 to t, they are allowed to diverge from their secular linear trend lambda g by an amount gamma t. But this gamma t amount that represents the deviation from the group's secular linear trend, you see that it's not indexed by g. So this deviation from the secular linear trend has to be common to every group. So that's why we call this assumption a common deviation from linear trends assumption. So parallel trends, you could call it a common trends assumption. This assumption is a common deviation from linear trends assumption. And by taking second difference of this equation, you can see that actually common deviation from linear trends is equivalent to having a parallel trend, a common trends assumption, a parallel trends assumption, but for the second difference of the outcome. Second difference is the difference between the 2 first differences. Okay. So under this type of common deviation from linear trends assumption, there is this paper by Mora and Reggio who propose the following estimator of the ATT, where the intuition is that instead of comparing out the first difference of the outcome from period 3 to 4, so 4, remember, is the period where treatment is implemented, instead of comparing the first difference from period 3 to 4 in the treatment and in the control group, we compare the second difference between, so the difference of the first difference from 3 to 4 and from 2 to 3 in the treatment and in the control group. And against the commonly held view, I don't know if it's commonly held, but the sometimes held view that allowing for linear trends is a little bit like cheating, because now the assumption is not testable anymore. Actually, this assumption is placebo testable, exactly as the parallel trends assumption is, by verifying that, and that's why I needed to have T and F equal to 4, because to be able to placebo test this assumption to be able to placebo test the standard parallel trend assumption, you need at least 2 pre-treatment periods. To be able to placebo test this assumption, you're going to need to have at least 3 pre-treatment periods. And so to placebo test this assumption, you're going to be checking that a second difference between the treatment and the control groups before treatment is not significantly different from 0. Okay, so when should we include control variables in the estimation of a Diff-in-diff model? So first, sometimes, perhaps because they have intuition coming from RCTs. So in the context of an RCT, we include control variables not to make the estimator more plausible. We know that in an RCT, the treatment effect estimator is unbiased for the average treatment effect, irrespective of whether we have covariates or not in the model. In the context of an RCT, the motivation to include control variables is to increase the statistical precision of our estimator. Okay? And so perhaps because they have this intuition in mind, sometimes researchers have this idea that in a Diff-in-diff as well, I should control because controlling is going to increase the statistical precision of my estimator. So we actually formally show in the appendix of this chapter that this intuition is misguided. Okay? If unconditional parallel trends holds, meaning that you do not need to control for the covariates, then including covariates in your estimation is actually going to weakly increase variance. So you're going to lose precision, actually. So gaining precision can never be an argument to include control variables in a Diff-in-diff model. So that means that the only argument to include control variables has to be that the conditional parallel trends assumption is more plausible than the unconditional one. Now, is it necessarily true that Diff-in-diff estimators with control variables are always going to be more plausible than Diff-in-diff estimators without control variables? So I would tend to argue that not necessarily, because including control variables opens the possibility for p-hacking and specification searching, in the sense that results can be sensitive to which control variables you include in the estimation. And then there's always going to be the concern that perhaps the researcher chose a given set of control variables because that allowed them to get a significant point estimate, or because that allowed them to get a point estimate of the sign that they were expecting the point estimate to be ex ante, etc., etc. So from an identification standpoint, estimators with covariates are more plausible than those without covariates because the identifying assumption is indeed weaker. But when we take into account estimation and the way the research process is done, it's actually not that clear that estimators with covariates are necessarily more plausible. And because, interacting with applied researchers doing Diff-in-diffs, we realize that sometimes researchers directly jump into estimating the model with covariates without even trying to estimate it without covariates first. We would like to make the following simple recommendation, which is that if you run your event study two-way fixed effects regression without controls, and when you do that, you find pre-trend estimators that are small, precisely estimated, then there is really no compelling reason to add covariates into the estimation, because if you do so, then the reader of your paper or the reviewer of your paper, when you send it to a journal, will always have will always wonder, okay, but how were those covariates actually selected? And, what tells me that actually results would not be different with different covariates. If, on the other end, when you don't have any covariates, the pre-trend estimators are either significantly different from 0 and large, or because, recall from the last sessions that significant pre-trend estimators is not necessarily a concern if you have very small but very precisely estimated pre-trend estimators, well, maybe they are significant, but we don't care. Then what matters is their magnitude relative to the actual event study estimators. But so if you have pre-trend estimators that are significant and large, or that are large and not significant, but very imprecisely estimated, then there might be more of an argument to include covariates into the estimation. Now, with this recommendation, what this means, by backward induction, and then this means that whenever we as referees see a Diff-in-diff estimator with covariates, that will now mean for sure that it's not that the researcher directly jumped into estimating the model. Right now, we don't know. We don't know whether the researcher did some specification searching or if they just did not try to estimate any other model. Now, if everybody adopts our recommendation, we will know for sure that this model is the outcome of a two-step specification searching model, which we know that pre-testing and model selection steps can lead to bias and size distortion for the post-test estimator that we eventually chose. Now, this is a concern that's at this stage, I feel a little bit theoretical, because it's been shown that it can bias estimators and distort, that pre-testing can bias estimators and distort inference. It's been shown in some contexts, but that are very different from Diff-in-diff estimation. And I think it's a little bit of an open question whether the type of model selection step that we are advocating for here could lead to large biases and size distortion in the Diff-in-diff context. Okay, so we've been going for an hour and 30 minutes. So maybe let's take a 10 minutes break and we'll resume.
Yeah, so my question is from the previous session on the two-way fixed effect. So you said when the ATT is heterogeneous, it's biased, or because of the negative weight. So heterogeneous, does that mean heterogeneous across time and also across groups? Or
could be both, actually.
Could be both.
TG. So here, actually, in the result we just saw, we have that units are only treated at period 2. So in that context, it's whether the TEG2, the treatment effects at period 2, vary across groups, okay? But more generally, for more general decomposition results of two-way fixed effect, we can have issue if treatment effects are heterogeneous across G or across T.
Gotcha.
So either just one side of heterogeneity can be.
So, but we're gonna see it's gonna depend actually. It's gonna depend on the design. So, but this we're gonna discuss that later actually.
Okay, thanks.
I actually also have a question. Let's say that the parallel trend holds unconditionally, so we don't need to include control variables, and we don't. But the effect is heterogeneous over X, which you don't include because we don't need to. Then that is fine, right?
Yeah.
Estimate correctly, right?
Yeah, absolutely. Yeah. Yeah, exactly. So heterogeneous effects, yes, across X is not a sufficient condition to actually control for X. Yeah, good point. Okay, so on the topic of control variables, I just want to say a few words about the case where we want to control for a very specific type of control, which is actually the baseline outcome. And that's something that people often do. They want to control for YG1 in their specification. And so in that case, the parallel trend assumption becomes this conditional parallel trend assumption, where we assume that untreated outcome evolutions from period 1 to 2 are a function of the period 1 outcome. But under this type of assumptions, the estimator that we're going to be using is no longer going to be a diff-in-diff estimator. Actually, it's going to become a matching estimator. Because intuitively, if you compare treated and control units, if you compare the outcome evolutions of treated and controls with the same outcome at period 1, you are actually just comparing the period 2 outcome of treated and controls with the same period 1 outcome. And this type of comparison, we want to be pretty careful when doing this type, when using this type of estimator, because they can lead to spurious results due to mean reversion, okay, which actually is an issue that was pointed out as early as in 1940 by this paper. And then there are these two more recent papers by Chabet-Ferrer and Doe and Hatfield that discuss it. I'm going to consider a very stupid model, a simplistic model to convey the intuition. So we're going to assume that the treatment has no effect, and the treated groups are such that their untreated outcome is either equal to 1 or to 2 with probability 1/2, while the control groups are such that their untreated outcome can either be 0 or 1 with probability 1/2. So you see that there is only one common value of the untreated outcome for the treated and the control groups, which is 1, okay? And then we assume that we have no serial correlation in the outcome. So then we have that the mean untreated outcome of is 1.5 for the treated groups, because 1 or 2 with probability 1/2, and 0.5 for the control groups. So in this DGP, should a researcher use a diff-in-diff estimator, or should they use a matching estimator conditioning on the baseline outcome? So the diff-in-diff estimator has this expression here. We compare the outcome evolution of the treated and the control. And the distribution in the treatment group, the distribution of the untreated outcome is the same as at both periods. Therefore, the expectation of this thing is 0. Same thing here. So the expectation of this estimator is 0, meaning that the diff-in-diff estimator is unbiased for the true average treatment effect, which is 0 in this example. Now, if we do the matching estimator, remember the matching estimator is comparing the period 2 outcome of the treated groups and the control groups that had the same value of the outcome at period 1. And therefore, that means that we restrict attention to groups with a period 1 outcome equal to 1, because that's the only common value between the treated and the controls. And then in that subsample, we compare the average outcome of the treated and of the control group. So is this going to be an unbiased estimator of the ATT? No, why?
Let's say the outcome is 1. Yeah, while groups in the control and make sure yes, so it's going to be the same outcome, and the same outcome would mean different reading states.
So at period 1 they have the same outcome, equal to 1, yes. But we've assumed that actually there is no serial correlation in the outcome. So at period 2, the treated group are going to go back to an average outcome of 1.5, irrespective of whether they were at 1 in period 1. And the control groups are going to go back to an average outcome of 0.5. Okay, so the expectation of this thing is going to be 1, not 0. So that's going to be biased. So of course, it's a very simplistic example, but that conveys the intuition of the problem of controlling for of the potential problem of controlling for the baseline outcome. Here, intuitively, you're restricting attention to the treated groups that got a bad outcome shock at period 1. And that's why their period 1 outcome is 1, which is the lowest possible value this group can get. And you're restricting attention to the control groups that got a very good outcome shock at period 1, because they have an outcome of 1, which is the best possible outcome that control groups can get. But now, if the outcomes are not perfectly serially correlated between period 1 and 2, at period 2, the treatment group are just going to go back to their higher outcome level, and the control group will just go back to their lower outcome level, which is going to create a spurious positive point estimate, but which is just due to mean reversion rather than to the effect of the treatment. Okay? And so this model is simplistic, but Chabet-Ferret and Doe and Hatfield, they provide more sophisticated and plausible examples where they show that this type of mean reversion phenomena can also occur, and whether they occur or not and whether they are going to be important or not depend essentially on the serial correlation of the shocks affecting the outcome from period to period. And at the end of the day, we recommend that if you really want to control for the baseline outcome, we don't necessarily recommend doing that, but if that's what you want to do, then you really need to do some type of placebo analysis to check that mean reversion is not leading to a spurious positive or negative treatment effect estimate. And so to do this type of placebo analysis, one way to do that would be to move the estimator back one period. So when you have several periods of data, the actual estimator is going to compare the outcome at the period of treatment of treated and controls with the same outcome one period before treatment. Moving that back one period, you can compare the outcome one period before treatment of the treated and control with the same outcome 2 periods before treatment. And if there is a mean reversion phenomenon that leads to spurious results, you'll be able to see it in this placebo analysis. And actually, this is so because Chabet-Ferret and Doe and Hatfield, they run simulations to document this issue, but actually it can happen in real applications. And there is this recent paper that revisits that revisits a published paper and shows that actually the supposedly positive effect of a reform in France in the original paper was actually spurious, was just due to the fact that the original paper was controlling for the lagged outcome, leading to some kind of mean reversion phenomenon. And once you don't do that, you no longer have an actual treatment effect. And this type of issue can also arise in a more subtle manner in cases where the assignment to the treatment or to the control group depends on the lagged outcome. So you could think of a reform where only firms whose number of employees is above a threshold the year before treatment are going to be eligible for the policy. And you're interested in the effect of that policy on employment of those firms the following year. Then the concern could be that some of the treated firms are treated just because in the year before treatment, they got a positive employment shock that put them above the eligibility threshold. But in the following year, they're going to revert to their lower, more secular employment level. And similarly, you could have control group firms that are in the control group just because in the year before treatment they got a negative employment shock, but in the following year they will revert to their higher secular employment level. And so in those cases, we think it's very important again to do placebo analysis to make sure that this type of mean reversion phenomena cannot bias the results. Here, a placebo analysis would amount to compare the F-2 to F-1 outcome evolution, so the outcome evolutions 1 year prior to treatment, among the firms that hypothetically, if the reform had taken place in year F-1, would have been treated based on their F-2 employment levels, and the control firms that would not have been treated in F-1 because their F-2 employment levels were too low. Okay. Yeah.
One question, final question on this. So suppose we do think that we need to control for control period outcomes, for example, because the covariates maybe are theoretically known but not well measured. Let's say the intuitive applied econometrician trick would be, okay, let's use more than one control period. How much averaging, if you have a good reason to think that this mean reversion has a time resolution that is small relative to the data that you have, how much can they address this problem? Because the test can tell you, but then the question is, okay, what to do?
Yeah, okay, so it's a very good point. So I did not detail that, but another possible solution is indeed to use lags further back in time, or to use several lags rather than one lag. And how many lags you should use, that's not clear. And and then, maybe the placebo can guide that a little bit. How many lags should you control for until you no longer have a spurious significant placebo coefficient? I also want to draw one very interesting connection, I think, with synthetic control. So synthetic control is, in a sense, a way to bypass this issue, because now you're matching the treated and the control not on one lag, but on the full history of all lags. And the justification, the theoretical justification of the synthetic control method assumes, to have results like consistency, asymptotic normality, etc., etc. You need to assume that the number of pre-treatment period is going to infinity, because that's what ensures that when you match treated and controls on an infinite number of pre-treatment outcome lags, of pretreatment outcomes, you are no longer matching them on idiosyncratic shocks, but on, you know, the secular factor model that's generating their outcome. But, you know, of course, the issue is that in practice, we rarely have very long panel data sets where we have a very large number of pretreatment areas. We sometimes do, but we do not always have such data sets. Okay. So I'm going to skip the application. Here, if you're interested, we have, you know, one simple example of a Diff-in-diff estimation with control variables. So we're not going to talk about interactive fixed effects and synthetic controls, but maybe I'm just going to go over our introductory paragraph on that. So those are clearly like interactive fixed effects or synthetic control methods. They are clearly like the, you know, the main very popular alternative to Diff-in-diff estimators. And the reason for that is that they do rely on an assumption that's really substantially weaker than the parallel trend assumption. They allow for differential trends between groups in a way that's that, you know, not fully non-parametric, but that's much less. The model for counterfactual time trends is much less parametric than that assumed by diffs-in-diffs. Now, it's still a literature that's under development, so there are still many open questions in that literature. And there's been recent important leaps, I would say, in this literature. For instance, the development of the synthetic DID estimator, which is a major progress in that literature, which we detail in the textbook. But even with those recent advancements, the state-of-the-art techniques, they still have some drawbacks. The main one is, like we discussed, those techniques are not as widely applicable as diffs-in-diffs estimators because they require a large number of pretreatment periods, T0. And how large should T0 be for you to be able to reliably use a synthetic control or a synthetic DID estimator? That's a bit of an open question. But for instance, in the synthetic DID paper, which to my knowledge has the best and most realistic simulations on the performance of those estimators out there, the authors actually consider cases where you have like something like 40 pretreatment periods. So it's not a small number of pretreatment periods that under which the estimators perform well. So another thing which, you know, may or may not be a problem, time will tell, is that those are papers that are often written very computationally. Like, you know, they propose an algorithm to compute an estimator, but they don't tell you what are the identifying assumptions underlying the estimators, which is a bit odd for econometricians or applied researchers. Again, I think there's been some progress on that, you know, like work by Bruno Ferman has several papers on synthetic control that clarify the assumptions. The synthetic DID estimator is also making its assumptions more explicit, but so that's another thing. And yes, and so a third issue is that those estimators, they often require choosing a tuning parameter. And there, even so, you know, like in the synthetic DID paper, which again is a huge advance on that front, in the sense that so there is a tuning parameter there, and they say, okay, the tuning parameter has to go to 0 at this rate, which is great because before we did not know the rate at which the tuning parameter had to go to 0, but still there is a constant in front of the rate that you need to choose. And there, you know, like the authors propose a constant that seems reasonable, that works well in empirical applications, but is it always going to work well is not that clear. And finally, the last thing that we want to be a little bit careful about is that in Diff-in-diffs, it's very easy to quote-unquote placebo test the identifying assumption via pre-trans test. It's a little bit less easy to do with synthetic control and synthetic DID estimator. There, the idea is essentially to say, okay, so rather than using all of our pre-treatment periods to estimate the model, we're going to leave out, let's say, 5 pre-treatment periods, estimate the model on the pre-treatment periods 1 to T0 minus 5, and then see that at pre-treatment periods T0 minus 4, T0 minus 3, etc., we still don't find treatment effects. So you can do that. That's not something that people always do. So I think that it's a little bit less systematic to test the identifying assumptions in the community of applied researchers that use synthetic control or synthetic DID than in the Diff-in-diff community. And also, as you can see, an issue with that is that the validity of synthetic control and synthetic DID relies on having a large number of pre-treatment periods. But if you want to do thorough placebo testing of your estimator, that means that you need to reduce even more the number of pre-treatment periods, because you need to leave a sufficiently large number of pre-treatment periods out of the estimation. Yes?
Having used that, just one further comment on that to clarify. The number of pre-treatment period is not just a data requirement. It has to be a number of pre-treatment periods that obey the same factor model in this case. And that can be further, they can be even more restrictive. One may have 40 years before the treatment in a data set, but one has to ask the question in whether in these 40 years the same secular trend to simplify holds. Otherwise, one just looks for a study. Let's apply the synthetic control. Well, we found this long series, but that's not enough.
Okay, no, very good point. And not so there is, when you compare the two methods, and it's a bit related to a discussion we had at the beginning of the class about, you know, like, should I worry if I have differential trends 20 years prior to treatment? Well, you know, less than if you have differential trends 2 years before treatment. In some sense, you can do Diff-in-diff estimation with parallel trends over for a short window around the treatment date, while to do synthetic control or synthetic DID, you need the linear factor model, which, okay, granted, is imposes less assumptions than parallel trends, but that model has to be true for a very long period of time. So I think it's a very good point that we will add to the book. Okay, so now let's start the second part of the class, where we're going to move beyond the classical design. Okay. So first, to motivate this, we're going to start by seeing a general decomposition result for two-way fixed effect estimators as soon as we get out of the classical design. So the running example, which I think you have the data set for that too, is a paper by Genskow and co-authors, so where they use a panel data set at the county times presidential election year level. So we have one observation every 4 years from the US, and they go from the 1872 to the 1928 election. And they want to assess if increasing the number of newspapers, if newspapers have a positive effect on turnout, if the newspapers encourage citizens' engagement in elections. And so for each county G and election year cell, they have the turnout in the presidential election in county G and in that election year. And they have the number of newspapers in county G ERT. And they're going to run a two-way fixed effects regression that's closely related to the one we discussed, even though not exactly. So I'll explain the differences later. But at this stage, what's important to realize is that the design of that study, the treatment variable in that study, is much, much more complicated than the one we've discussed so far. The treatment is non-absorbing. So, you know, the number of newspapers in a county can change multiple times. You have newspapers that open, newspapers that close. The treatment is also non-binary. Of course, the number of newspapers is actually a discrete treatment variable that in the data, I think, ranges from somewhere like from 1 to 40 or something like that, from 0 to 40. And also, we have variation in treatment timing in the sense that not all counties experience changes in their number of newspapers at the same point in time. So the data that we use is the Gensko et al. DID textbook, which has a county identifier, a state identifier, an election year identifier. We're going to have also a state times election year identifier, the outcome, the turnout rate in county G election year T, the treatment, the number of daily newspapers in county G election year T, and the first difference of the outcome and the first difference of the treatment. So in this chapter, we are going to momentarily assume that we have no dynamic effects. And so far, whenever we assume no dynamic effects, this was just to simplify notation. Now, actually, this is not just to simplify notation. This actually has consequences, but we make that assumption to be consistent with the two-way fixed effects regression. So the two-way fixed effects regression is YGT on group fixed effects, time fixed effects, and DGT. And you can see that in the regression, we do not include DGT minus 1, DGT minus 2, etc., etc. We do not include the lag of the treatment in the regression. So implicitly, this regression is ruling out dynamic treatment effects. And so to be consistent with that regression, we are going to analyze it in some sense to not be unfair with that regression. We're going to try to analyze it, maintaining some of the implicit assumptions it's making, namely that there are no dynamic effects. And so in the newspaper example, that means that the turnout in county G ERT can depend on the number of newspapers available in that county and in that year, but not on the number of newspapers that were available in the previous election season. So now that we consider potentially non-binary treatments, we need to redefine our GT-specific treatment effects. So before, we had just defined them as expectation of Y1 minus Y0, but now that we have non-binary treatments, for any cell that does not have a treatment of 0, we are going to let TGT be the expectation of its observed outcome, which is YGT under its actual treatment of DGT, minus its counterfactual outcome without any treatment. And we scale that by DGT to get a slope parameter. Okay, so that's the slope of the potential outcome function of cell GT between a treatment of 0 and its actual treatment. So in the newspaper example, if we have a county year that has 4 newspapers, we are comparing the outcome, the turnout in that county year under its actual number of newspapers, 4, minus what would have happened to it with 0 newspapers, and we scale that by 4 to get a measure of an effect per newspaper. And then we know that we cannot unbiasedly estimate those consistently, estimate those effects because they apply to only one group. So we need to aggregate, and a very natural way to aggregate here is just to aggregate all the TGTs across the treated cells, and that gives rise to our ATT parameter. Okay, so we're gonna let WGT be equal to U at GGT divided by the sum across all the treated GT cells of their U at G prime T prime times D G prime T prime. And U at GT is going to denote the sample residual from a regression of the treatment DGT on group and period fixed effects. So just to make things a bit more concrete, in the newspapers example, how could you compute those residuals U at GT?
Predict this numbers of your state.
Yeah.
Stuff.
Yeah, exactly. So you would just, exactly. So you would just regress the newspapers on county fixed effects, ER fixed effects, and then you would compute the residual from that regression. Okay, and then we have the following result, that under our no anticipation and no dynamic effects assumption and parallel trends assumption, then E of beta at Fe is equal to the sum across all the treated cells of WGT times TGT. So I would like you to interpret this result in general and in the context of the newspaper's example. So what is beta at Fe unbiased for?
That's
Yeah, exactly. So I'm going to say weighted sum rather than weighted average of effects. But yeah, so we take the treatment effects of all the treated cell, and then we take a linear combination of those, pre-multiplying them by WGT. So if you want, you take the vector of treatment effects, you take the vector WGT, and it's like the inner product of the two. That's the dot product of the two. That's at this stage, that's what we can say. So if we sum the WGTs across all the treated cells, what's the value of that sum? Looking at the definition of WGT, if you sum the WGT across all the treated cells, what's going to be the outcome of that calculation? 1, exactly, because you're going to get numerator divided by denominator. Okay, so then this shows that beta at Fe is unbiased for a weighted sum of treatment effects with weights that sum to 1. And because the weights sum to 1, then that means that the average value of the WGT weights across the N1 cells is 1 over N1. Okay. So a consequence of this result is that outside of the classical Diff-in-diff design, the two-way fixed effect estimator could be biased for the ATT under a no anticipation and a parallel trend assumption. So to have that for any possible values of the treatment effects T, GT, we have that expectation of beta at FE is equal to ATT. Then we need to have that WGT is equal to 1 over N1 for all the treated GT cells, meaning that the WGTs do not vary. All the treated GT cells have the same WGT. Whenever WGT varies across the treated cells, then we're going to have that, because on average, the WGT are 1 over N1, then for some cells, WGT will be greater than 1 over N1. For other cells, it will be lower than 1 over N1. And then we could have that beta at FE is biased for the ATT if the cells whose effect is upweighted by the two-way fixed effect estimator with a weight greater than 1 over N1 have a different treatment effect than the cells that are downweighted by the two-way fixed effect estimator. So now having that WGT is equal to 1 over N1 is constant, is equivalent to having that the numerator of WGT, because the denominator of WGT is a constant, then WGT is constant if and only if its numerator is constant, and the numerator is this quantity here. Now, so let's try to, what's going to help us a bit is to get a closed form expression for this residual. So U at GT is the residual from a regression of DGT on group fixed effects and time fixed effects. The coefficient on the group fixed effect is in this regression is actually simply going to be the average treatment of group G across all time periods, which we're going to denote by DG dot. And similarly, the coefficient on the period fixed effect, on the period T fixed effect, will be the average treatment at period T in across all groups, which we're going to denote by D dot T. Then so U at GT is a residual, so it's DGT minus the predicted value for DGT according to the regression. And therefore, U at GT will be DGT minus the prediction, which is DG dot, the coefficient on the fixed effects for group G, plus D dot T, which is the coefficient on the period T fixed effect, minus, but then the minus becomes a plus, D dot dot, which is the average treatment across all groups and time periods, which you can think of as being the intercept in the regression of DGT on group and period fixed effects. Okay, and now with this expression, we have that DGT times U at GT as this expression here. So now in a classical design with an absorbing binary treatment and no variation in timing, DGT, DG dot, and D dot T are all constant across the treated cells. Because any treated cell has DGT is equal to 1. All the treated groups are treated for the same number of time periods because there is no variation in treatment timing. Therefore, DG dot is constant also. And D dot T is also constant because for any time period where the treatment takes place, the same proportion of groups are treated, again, because we have no variation in treatment timing. Okay, and so that shows that in design 1, we have that the weights are constant. And that's not surprising. We already saw that result. That's just, a way of reproving a result we saw earlier. We saw earlier that in a classical design, the two-way fixed effect estimator is unbiased for the ATT under no anticipation and parallel trend assumption. By the way, if a reviewer of one of your papers asks you to implement an heterogeneity robust Diff-in-diff estimator while your application is a classical Diff-in-diff design with binary treatment, no variation, timing, etc., you can refer them to, now it's been said in multiple places, I think by us and by others, that in this case, it's not necessary. But because like I was saying earlier, so I've heard those stories often that people now ask, even in designs where it's unnecessary, they ask people to estimate heterogeneity, to compute heterogeneity robust estimators. The funniest story was a case where the researcher, does it, and of course ends up showing estimators that are numerically equivalent to those from the classical two-way fixed effects regression. But then the reviewers did not believe them. They thought that they had manipulate that for the heterogeneity robust to estimators to be numerically equivalent to two-way fixed effect, they must have, manipulated the data one way or another. So there is these things have overshooted a little, have gone a little bit overblown. Two-way fixed effects estimators do not always have issues with in the presence of heterogeneous effects. So now, writing this textbook, our conjecture was that there would be an if and only if relationship between having that all the weights are constant and being in a classical Diff-in-diff design. But actually, writing this textbook, we realize it's not true. You can have other designs than the classical Diff-in-diff design where the weights are constant. And here we give an example where the treatment is non-absorbing. So groups can go from into and out of treatment at various points in time. But there is no variation in treatment timing, okay? Meaning that all the treated groups go in and out of treatment at all points in time. And when we have, on the other hand, when we do have variation in treatment timing or treatment dose, in most cases, the numerator of the weights, and therefore the weights, varies across treated cells. Because if we have variability in the treatment dose, then DGT might vary across treated cells. And if we have variation in treatment timing and or dose, DG dot and D dot T will also vary, and therefore we will not be unbiased for the ATT. Yes?
Regarding what you said for design one, the simple case, and not to use heterogeneous robust treatment, Diff-in-diff estimators, I guess the two-way fixed effect has also the advantage of being more efficient compared to these robust
well, in that case, because they are numerically equivalent, it will not be more efficient because, if two estimators are equal, their variance as equal. The advantage there is still one advantage, which is computationally, because it could be that, especially if your data is huge, it could be that that the heterogeneity robust estimator now gives you a computationally totally inefficient way of computing the two-way fixed effect estimator. Okay. So now I would like you to find an additional assumption. So under no anticipation and parallel trends, we have that beta at FE is not unbiased for the ATT. Can you find an additional assumption such that if you add that assumption to all those that are here, then you would get that beta at FE is now unbiased for the ATT? Yeah, exactly. So if you assume that there exists some real number delta such that TGT is equal to delta, meaning the treatment, coming back to your question, meaning that the treatment effect does not vary across G or across T, then you get that beta at FE is unbiased for the sum of the WGT times delta. You pull the delta out of the summation, the weight sum to 1, therefore beta at FE is unbiased for the constant treatment effect parameter. So you see, when you have a regression coefficient that's estimating a weighted sum of fx with weight summing to 1 that at least guarantees that if fx are homogeneous, this estimator will be unbiased for the homogeneous effect parameter. Okay, and we're going to see. I mean, I don't know if we'll have the time to see them together, but there are other estimators that have been used in, you know, these causal inference, panel data type applications, where that do not estimate weighted sum of fx with weight that sum to 1. Okay, so at least this one does. So now, of course, the homogeneous effect assumption is quite strong and maybe implausible in quite a few scenarios. So for instance, in the newspaper example, you could say that the effect of newspapers on political engagement could differ in rural counties and in urban counties, because maybe in urban counties, people have other ways than reading newspapers to communicate information and get engaged politically, while in rural areas, the newspapers could be playing a bigger role. You know, you can always like cook up this type of stories, but so it does not seem to be like a super appealing assumption. Now, there's going to be another weaker assumption under which beta at FE is unbiased for the ATT, which is stated in this equation 5.9 here. So this essentially says that the covariance between WGT and TGT is equal to 0. Because this is the sum of the difference between WGT and their average, 1 over N1, times the treatment effects minus their average. So this is really the covariance between the weights and the treatment effects. So if the weights are uncorrelated to the treatment effects, then the fact that we estimate a weighted sum of effects does not really matter, because the effects that get upweighted by the two-way fixed effect estimator and the effects that get downweighted do not systematically differ. And at the end of the day, we're still estimating the ATT. So now let's try to assess a bit the plausibility of this. And this is strictly weaker than assuming constant effects, because if you have constant effects, then this condition automatically holds. Okay. So let's assess a bit the plausibility of this condition. And for that purpose, we're going to momentarily assume that the treatment is binary. And then in that case, the numerator of WGT is equal to that expression here, okay, to 1 minus dg dot, the average treatment of group G, minus d dot t, the average treatment at period t, plus d dot dot. Under which economic model of selection into treatment could we have that this quantity is actually correlated with the treatment effects, which would then imply that our no correlation condition actually fails? Yeah, exactly. If you believe that GT cells choose to get treated following a Roy model, so a Roy model is a model where you choose to get treated when the benefit from getting treated is greater than the cost, and oftentimes, in at least in the canonical original version of the Roy model, we assume that the benefit from being treated is y1 minus y0, the treatment effect. Then the cells, the groups where the effect of the treatment is the largest are going to be the groups that get treated the most often. And therefore, their dg dot is going to be greater. And therefore, the two-way fixed effects regression will give less weight to the treatment effect in those cells. Okay, So under a Roy selection model, there might be some correlation between treatment effects and the weights. So this no correlation condition might not be very plausible if treatment follows a Roy model, but there might be other cases where actually this condition is more plausible. So interestingly, this condition is sometimes testable, actually. The no correlation condition is actually sometimes testable. We'll see that in the next chapter. For now, we just propose placebo test of, or suggestive test of this assumption. If you observe a proxy variable PGT that's likely to be correlated with the treatment effect. So in my example, actually PGT could, for instance, be the population in county GERT. If you think that more rural and more urban counties are likely to have different treatment effects, then PGT could be the population of county GERT. And then you can test if the weights WGT are correlated with the population of GT as a suggestive test of this no correlation condition. Okay, so beta hat is not necessarily unbiased for the ATT unless we are willing to impose this no correlation condition. Now, do we have that the weights WGT are necessarily positive for every GT? No, not necessarily, because they depend on this U at GT residual. And the U at GT residual could be negative. And in fact, it's going to be negative. You're going to have some negative weights whenever there are some treated GT cells, such that dGT plus d dot dot, the terms that enter with a positive sign in U at GT, is strictly lower than dg dot plus d dot t, the terms that enter with a negative sign. Okay? And so what this means is that groups that are treated the most are more likely, meaning that they have a high dg dot, are more likely to have some of their effects weighted negatively. And time periods at which the most groups are treated are also more likely to have that, to be such that some effects at those time periods are weighted negatively. So why is it not appealing to have negative weights? Well, that's because in the newspaper example, we could be estimating something like 3 times the effect in county A minus 2 times the effect in county B. And then if you assume that in county A, one more newspaper raises political participation by 1 percentage point, but in county B, the effect is also positive, but one more newspaper raises participation by 2 percentage points, then what two-way fixed effect is estimating is 3 times 1 percentage point minus 2 times 2 percentage point, which would tell you that one more newspaper decreases political participation by 1 percentage point. So this shows that beta at FE may not satisfy what's called the no sign reversal property. Okay, no sign reversal property means that if the treatment effect is of the same sign for everyone in the population, if the treatment effect is positive, let's say, for everyone in the population, then the expectation of my estimator should also be of that sign. So it's a very, very minimal requirement on a treatment effect estimator. It's much weaker than requiring, let's say, that my estimator is unbiased for the ATT. It's a much weaker criterion. And just asking that if all I ask from an estimator is no sign reversal, then all I'm asking for is that if everybody benefits from treatment, I cannot end up saying that the treatment had a negative effect. Yeah.
Is this the, I don't remember the name of the assumption related to the first stage of an instrumental variable?
Monotonicity?
Yeah.
No. It's
Okay.
not. Okay. No, I see your point. So, cosine reversal is a concept that's defined under the assumption that we have a monotonicity assumption. Yeah. So yeah, no, there is indeed a connection that we. So it's but it's not really used for the same purpose. Here it's like, let's assume that even if we add monotonicity, then if we don't have sign reversal, then the estimator could be misleading. So it's used as a way to introduce a measure of sensitivity of the estimator. Yeah. Yeah.
Here, D can be is discrete, right? It's not necessarily binary, right?
Yeah,
Or
it
it's
could be
also
anything at this stage. Could even be continuous.
So as far as I know, it's the groups that are treated with the lowest dosage are the ones that are going to receive more likely negative weight also, right? Yeah. And this is coming from DGT, I guess, because the highest
Yeah,
exactly. Because the highest dosage will have high DGT, therefore will have less likely
No, that's
a negative weight, correct?
Yeah, absolutely. Actually, yeah.
It's coming from there.
Yeah. Okay, yeah. Let me take notes of that up, because it's coming from this part used to be in the chapter where we would assume binary treatment, but you're right that with a non-binary up. Okay. Okay, so now let's see a few extensions. So this result that we just saw comes from a paper by Xavier and I. And in that paper, it's been a long journey to get to that result. And here there is at least in our opinion, the steps of that journey. And so in that paper with Xavier, we also consider different regressions. We also consider, for instance, the coefficient of the treatment in a first difference regression of the outcome change on the outcome change and period fixed effects. This type of estimators is very closely related to the two-way fixed effect estimator in the sense that with two time periods, actually, the two are numerically equivalent. So that's a well-known result, that with t is equal to 2, first difference or two-way fixed effects are numerically equivalent. Now, with t greater than 2, the two are no longer numerically equivalent, but we show that the first difference estimator can also be under the no anticipation and parallel trend assumption. We have a very similar result than for the two-way fixed effect estimator. This estimator can also be decomposed as a weighted sum of the TGTFX with weights that sum to 1. But the weights are no longer the same. The weights, so that's why we denote them by WFDGT. So the weights are the weights are of course the same when t is equal to 2, because then the estimators are the same. But when t is greater than 3, the weights can be different. But they also sum to 1, and they may also be negative. Okay. And an interesting consequence of this result is that actually we have a testable implication of the constant effect assumption. So what's the testable implication of the constant effect assumption? So the weights are not necessarily going to be equal. So the weights are going to be different. So the two sets of weights sum to 1 indeed, yeah. But using the fact that the weights sum to 1, both set of weights that could differ, but they both sum to 1, what is going to be if we have constant treatment effects?
Similar to the previous.
Yeah, exactly. So the expectation of beta at FD is going to be the same as the expectation of beta at FE. They are both going to be unbiased for the constant treatment effect parameter. So actually, that means that if you want to test whether treatment effects are heterogeneous or not, you can compare your fixed effect and your first difference estimator. And it's a first diagnostic check of whether heterogeneous effects could bias your two-way fixed effects regression. Well, you can start by seeing if results change a lot when you run the model in first difference. Okay, and in that same paper with Xavier, we also derive a decomposition of two-way fixed effects regressions, but with control variables, which we actually already discussed because their negative weights can arise even when negative weights and the fact that the estimator is not unbiased for the ATT, those two phenomena can even arise in the classical design. But we also have a result for two-way fixed effects with controls in general designs. Okay, so a potential diagnostic tool to ascertain whether to see if your two-way fixed effects regression can be robust in the presence of heterogeneous effects is to compute the weights attached to the regression. And to do that, we have a two-way FE weights Stata and R command. And so the syntax of the Stata command is as follows. So it's two-way FE weights, your Y variable, your group identifier, your time identifier, and your treatment. And then there is this option type that you need to specify because the command can compute several decompositions of two-way fixed effects regressions. And so if you want a decomposition of the two-way fixed effects regression, you need to input the FETR argument into the option. If you want to decompose instead a first difference regression, the argument has to be FDTR. And then the argument of the type option has to be FDTR. But then you also need to specify your first difference outcome as the outcome, your first difference treatment as the treatment. And in that case, actually, the command needs a fifth argument, which is not the first difference treatment, but the treatment itself, because actually those WFD-GT weights depend not only on the first difference of the treatment, but also on the treatment itself. If you want to decompose two-way fixed effects or FD regressions with controls, there is the controls option where you impute the control variables. And finally, if you want to run the suggestive test of this assumption that the weights and proxies for the treatment effects are unrelated, you can specify the test random weights option, because we view this assumption as an assumption as essentially saying that the weights are as good as randomly assigned, and so hence the name of the option. Okay, so now let's revisit an empirical application. So this Genskau et al. Paper that we talked about, they estimate a regression very similar to our baseline two-way fixed effect, but there are two differences. The first one is that they have some control variables in the regression in the form of state year fixed effects. So they want to allow for state-specific trends. So they assume that counties are on parallel trends within states, but they allow for differential trends across states. So that's the first difference. And the second one is that they estimate the regression in first difference rather than estimating it in levels. So in our replication, we're going to start by considering a regression, the baseline two-way fixed effect in levels without controls. And we're gonna decompose that regression. We're gonna compute the weights attached to that regression. Then we'll move to two-way fixed effects with the same controls as they do. And finally, we will consider the regression in first difference with the same control. Okay, so the first question, you need to use this data set, and then you're going to regress turnout on the number of newspapers and the county and year fixed effects, and you're going to cluster standard errors at the county level. So according to the regression, do we have a positive effect of newspapers on participation, no effect, or a negative effect? Yeah, exactly. So up. So you see in that regression, that's the coefficient on newspapers, which would indicate that one more newspaper raises turnout by 0.29 percentage point. And it's a little bit at the limit in terms of statistical significance. Okay, it's significant at the 10, but not at the 5% level. So then we use the two-way FE weights command to decompose the regression. So the syntax is two-way FE weights outcome group identifier time identifier treatment with this type FETR option to ensure we decompose the baseline two-way fixed effects and not, let's say, a first difference regression. And so what he says is that under the common trends assumption, the two-way coefficient, which is equal to what we saw earlier, which is a good sanity check to make sure that you're decomposing the coefficient that you think you're decomposing. Here, that's the case because that matches with the coefficient here. Estimates a weighted sum of 10,378 effects, where 6,180 effects are weighted positively and 4,198 are weighted negatively. And the comment also gives you the sum of the positive weights and the sum of the negative weights. And so as predicted, the sum of the WGT is 1. But we have that the sum of the positive weights is 1.47 and the sum of the negative weights is minus 0.47. So that shows that in this example, the regression is not estimating the ATT, And it's also not estimating a convex combination of effects, convex meaning weighted sum with only positive weight. And it's pretty far, like it's also, that's a question we got a lot at the beginning, like I have like minus 0.05 of negative weights. Is it a lot? I have minus 2 of negative weight. Is it a lot? It's always hard to draw a line. I mean, minus 2 of negative weight is clearly a lot, I think. But here, that's substantial enough that you can say that you're pretty far from estimating a convex combination of effects. Okay, so now let's move on to let's yeah.
I might have missed this, but aren't these weights stochastic quantities? Because they depend on D, and D is a random variable. So you made, this, you talked at the beginning about the several designs about inference. So if I get a weight which is minus 0.001, so is negative, it's close to 0, and is a random quantity, do I test if this is equal to 0 or not?
So, okay, so several answers to that. So first, in the perspective we're adopting, the design is conditioned upon. So the design is not random, and therefore the weights are not random. Now, so what we're gonna, I don't think let's see if we see it or not. Maybe given your question, I will show a result along those lines. The results about negative weights can change quite dramatically if instead of conditioning on the design, you no longer condition on the design. And on top of that, you assume that the treatment is, let's say, as good as randomly assigned, or not necessarily the treatment per se, but the treatment timing is as good as randomly assigned, etc. In that case, actually, there's going to be cases where conditional on the design, you have negative weights, but unconditionally and with as good as random treatment, all the weights are positive. Okay. But what's important to realize is that it's not only to have this type of results, you do not only need to stop conditioning on the design. You also need to assume that the way the treatment is assigned is known to you, and there is an element of randomness into it. If you were to just take, like the sampling-based perspective, where the design is no longer conditioned upon, but you have no clue as to how the treatment is being assigned, that would not dramatically change the results that we are seeing here. It would still change those results in the sense that looking at the individual value of the weights would not really make sense anymore. But for instance, things like looking at the correlation across all the treated cells between the weights and some observables would be well-defined exercises. And, even like looking at aggregate statistics, like the sum of the positive weights or the sum of the negative weights, that's still a well-defined exercise, because then you can, for instance, run a statistical test that the sum of the negative weights is significantly negative. And if it is, then you can reject the null that you're estimating a convex combination of effects. You could test the null that the weights are all equal to 1 over n1. That's also a well-defined null. And if you reject it, then you can reject the null that you're estimating the ATT. You see, so it would just change a little bit the testing problems, but not fundamentally. Fundamental changes would happen if you're no longer conditioning on the design and you assume the assignment is known. Okay. Okay, but very good question. So, okay, so now let's move on to the second regression, where we start controlling for state year effects. So I start by generating dummies for each possible value of the state year variable, and then I run my regression. And the regression up now, I have many fixed effects in my regression, so it takes a bit of time to run. But you see that actually including the state here effects drastically changes the result. Like now we have a negative and insignificant point estimate. And if I decompose, so actually I'm not going to do it because of the controls, it's going to take like maybe a minute or so. And the results will be essentially the same as those results here. But now let's move on to the regression actually estimated by the authors, which is the first difference regression with state here fixed effects. Okay. When you do that, now I mean so it's really strange actually this application, because now the point estimate is almost exactly back to the first one with the regression in levels without the state here effects. And now it's very statistically significant. I mean, statistically significant at conventional levels in social sciences, not in physics. Which might be why they have a bit less, they do a bit less mistakes in physics. And then we can decompose this first difference regression. So we change the FETR argument to FDTR, and we change the outcome to its first difference, treatment to its first difference. We still need to also have this fifth argument for the treatment. And then, yeah, that one is a bit slow, actually. So let's see if it takes too long. Maybe I'll go to the PDF. So what that would tell us is that, again, unsurprisingly, we're estimating a weighted sum of effects with many negative weights. And now, actually, the sum of the negative weights is much larger than before. Now, we are really very far from estimating a convex combination of effects. The negative weights sum to minus 1.43. And now, yeah, okay, which is what we have here. And now let's assess if actually the weights are correlated with things that could predict treatment effects. And here I'm going to try one very simple thing, which is to see if the weights are correlated with the year variable. Because we could assume that treatment effects are changing over time. Maybe people are becoming more literate over the literacy rate is increasing over the period. So the average readership per newspaper could be increasing, and therefore newspapers' effects could be increasing. Or alternatively, you have at the very end of the period, but still you have a new very important mass media that appears, the radio, that could diminish the effect of newspapers. So, there are reasons why the effect could be changing over time. And when we do that, we're going to find that actually the weights are negatively correlated with the election year, which is not totally surprising because the weights, remember, they have this D.T term in them, which is the average treatment at year T. Newspapers keep developing over the period, so D.T is probably increasing with time, which means that the weights are diminishing with time. So that's essentially what we are getting here. And so that's really an example where we're estimating a very non-convex combination of effects. The fixed effects and first difference estimators can be very different. Like if we make an apple-to-apple comparison, namely we compare the two specifications with the state year controls, then we have one coefficient that's positive, significant, another coefficient that's negative, and actually we tested the two coefficients are very significantly different. So that's an indication that we do have heterogeneous effects, because we saw that if we did not have heterogeneous effects, the two coefficients should be the same. And the weights are correlated with a variable that's likely to be correlated with treatment effects. So that's really, not all two-way fixed effects applications are such that you want to move away from two-way fixed effects and use an heterogeneity robust estimator. But here, in this case, we have sufficiently, many signals that the regression could be biased if we have heterogeneous effects, and that we may want to use instead a robust estimator. Okay, and so to conclude before lunchtime, so the roadmap for what comes next is that in the next 2 chapters, we're going to focus on 2 seemingly very small departures from the classical design. In chapter 6, we will see designs where we have a binary absorbing treatment, but with variation in timing. And in the next chapter, we will consider the case where we have an absorbing treatment, no variation in timing, but the treatment is non-binary. And we will see that in both cases, this is enough to generate situations where two-way fixed effects can be biased for the ATT, can estimate non-convex combination of effects. We will see why, and we will see that in both cases, the problem is coming from the fact that two-way fixed effect is using a Diff-in-diff estimators with a control group that's actually treated. That's the source of the problem. And then we will see that then once we've understood the problem, it's going to be very easy to propose heterogeneity robust estimators that do not suffer from this problem. And then in the last chapter of the book, which I don't know if we'll have time to see together, we will combine the insights from designs with variation in timing, designs with variation in dose, to actually propose robust estimators in general designs where we could have a non-binary and or non-absorbing treatment. Okay, and we'll start doing that after the lunch break.
When we haven't seen the lunch yet, it's
okay.
It's not still also. It's a good moment to ask.
I had a question on the first part actually of the course when we were talking about nonlinear models to do difference in differences. We know that in nonlinear estimation models, there's usually some issues with interpretation of coefficients of interaction terms.
Yeah.
So I was wondering if we should be wary about that in some way, or
Yeah. Okay. So exactly. So I think so. I'm not. I don't recall the details of this debate all that well, but maybe let me search. You can sway in India. Okay, so I think you're referring, in fact, to this paper. And this paper it's a bit related to, the difference between marginal effects and average effect, etc. So if you're interested, it always depends on what's your target parameter. People sometimes start arguments just because they talk about different things. So if what you're interested in is the average effect of the treatment on the observed Y variable, then that's what you should compute. Yeah, because that's giving you an estimator of the average Y1 minus the average Y0. If that's not what you're interested in, if what you're interested in is the effect of the treatment on the latent outcome in the probit or the Leuclid model, which might have a structural interpretation as, the utility that you derive from being treated versus untreated. Then what you should look at is this thing here. Okay, so it all depends on what you're interested in. And I don't really remember, there was a second paper involved in that controversy, which is not cited here because here, we're mostly doing reduced form and not looking at the, more structural interpretation of things. But yeah, that's... And the very famous paper by Embrace in the journal in the JBS, where he says that you should never use. So I think where he says that you should never use nonlinear models. That's again it depends. Like if you're interested in the structural interpretation, then maybe you want to use the nonlinear model. But actually, here, this type of equations and scenarios, they show that even if all you care about is the reduced form E of y1 minus y0 effect, you might still want to use a nonlinear model. Okay, so let's start again. So now we're going to start our study of designs where the treatment is still absorbing and binary, but we have variation in the treatment timing. And as a shortcut, we're going to refer to those designs as binary and staggered. And so in a binary and staggered design, we have that the GT satisfies this equation. So you see that the only difference with respect to the classical design is that now F, the first treatment date, has become G-specific. So groups can vary in terms of what is the first date when they become treated. And so if we have a group that's never treated, we let FG, their first treatment date, actually be T+1 to reflect the fact that actually they're never treated. So the running example in the chapter is going to be the effect of unilateral divorce laws, UDLs, on the divorce rate. And so the setting is that between 68 and 1988, we have 29 US states that have adopted one of these laws, which allow one spouse to terminate a marriage without the agreement of the other spouse. And so Wolfers, building upon prior work of Friedberg, uses a yearly panel data set at the state level in the US, running from 56 to 88, to estimate the effect of those laws on the divorce rate. And the treatment in this setting is a binary treatment. You have or you don't have the law. It's absorbing because none of the states during the study period actually repealed one such law after having adopted it. And there is variation in treatment timing, okay? Because those 29, so first, there were actually 2 states that had already adopted one such law in 1956, but then the 29 states that adopt during the study period do so at different dates. So the data that we're going to use for this chapter is the Wolfers DID textbook dataset, which has a state and a year identifier, a cohort identifier, which is equal to the year when a state adopted the treatment, which is our FG. The only difference with the textbook is that in the data, FG is equal to 0 and not to F+1, to T+1 for never treated states. Then we have this early, late, never variable that's equal to 1 for states that adopt earlier than the median, 2 for states that adopt but later than the median state, and 3 for the never adopters. UDL is the treatment, equal to 1 if a state year is treated. Exposure length is equal to the number of years at date T for how many years has state G been exposed to the treatment. Then we have relative time indicators. Rel time 1 to rel time 15 are indicators for whether state G at day T has been treated for 1 year, for 2 years, etc., all the way to 15. And the last one, rel time 16, is an indicator if at year T, state G has been treated for at least 16 years. And then we have the same thing, but for relative time before the treatment. So rel time -1, for instance, is an indicator if cell GT is such that state G is going to be treated in 1 year from now. The outcome is the divorce rate per 1,000 people. ST-pop is the population of state G in year T. And ST-pop 1968 is the population in the baseline year. And control group is a variable for the never treated groups. Okay, so in binary staggered designs, we're going to redefine a bit our target parameters. So remember that bold 1k is a vector of k1s. And in a binary and staggered design, so our TGT are, as before, the expectation of YGT minus the observed outcome minus the never treated outcome. And in a binary and staggered design, this TGT is actually an effect of having been treated for T minus FG minus 1 periods rather than untreated. Then we can define our ATT as before as the average of the TGT effects. Out of convenience, we are going to also index group-specific effects. Instead of indexing them by calendar time, we are also going to index them by length of exposure, namely relative time since the start of the treatment, hence the superscript R for relative. So TGL is going to be the effect of the treatment in group G at date FG minus 1 plus L, namely L periods after adoption. So that's an effect of having been treated rather than untreated for L periods. Then we can define our more disaggregated target parameters than the ATT, the ATTL effects, which are the average effect of L periods of exposure to treatment across all groups for which we're going to be able to estimate those effects. So what does that mean? Well, that means first that the group needs to be observed with L periods of exposure to treatment before the end of the panel, before big T. So FG minus 1 plus L has to be lower than big T. But actually, FG minus 1 plus L, the period when that group reaches L periods of exposure, has to arrive at a time period where we still have at least one group that's untreated that we can use as a control group. Okay, so that leads us to define this underline T quantity, which is the last date when there is still at least one group that's untreated. And if you have never treated groups, then this underline T period is just big T, the last period of the panel, but it could be earlier than T. Okay, so to be able to estimate those TRGL effects, we will need that FG minus 1 plus L happens before underline T. So that's why we restrict attention to groups satisfying that condition. Okay, and if we have no group treated at period 1 and we have never treated groups, then we have the following relationship between the ATT and the ATTL. The ATT is just a weighted average of the ATTL effects. So we already discussed that if, without assuming that the effect of the treatment does not change with calendar time, then the function that maps L into ATTL cannot be used to determine if the effect of the treatment varies with length of exposure. And the reason for that is that ATT1, for instance, measures an effect of one period of exposure, but when groups adopt, while ATT2 measures the effect of 2 periods of exposure, but the period after groups have adopted. And so there are therefore two differences between ATT1 and ATT2, the date of measurement, calendar time, and the number of periods of exposure. Now, there is one more caveat that arises when interpreting the event study function in designs with variation in treatment timing. So even if the treatment timing, if the treatment effect does not vary with length of exposure or with calendar time, it's constant across both dimensions, could we still have that ATTL differs from ATTL prime? Yes, why? Yeah, exactly. So now a further issue is that, the groups that meet this condition are going to change with L. You're going to have fewer and as L grows, you're going to have fewer and fewer groups that reach their health periods of exposure to treatment before that threshold here. Okay. And we're going to see that some of the Stata and R commands that we're going to discuss to implement Diff-in-diff estimators in designs with variation in treatment timing, they have options that allow you to keep the composition, to avoid these compositional effects, to make sure that all of your event study effects are estimated for the same set of groups, which, might come with a price in terms of precision, because that means that you're going to be able to estimate the first study effects for a smaller sample. But if you want to avoid those compositional changes, that can be achieved. Okay, but before talking about Diff-in-diff estimators, let's start talking about two-way fixed effects estimators. So first, we're going to do as we did in chapter 3. We're going to start with the static estimator and then the event study one. So we have, in the previous chapter, we saw a very general result, decomposition result of two-way fixed effect estimators under no anticipation and parallel trends. Of course, this result still applies in the binary and staggered case. It's just that in this case, the weights simplify a little bit. So first, remember that in general, the weights WGT are dGT U at GT divided by the sum of dGT U at GT. But now, in a binary treatment case, all the treated have a dGT is equal to 1, so we can forget about dGT. And then we also have that in a binary and staggered design, we have that dG dot, the average treatment of group G, is just the number of periods over which it's treated divided by T, and the number of periods over which it's treated is just T minus FG plus 1, because the treatment is absorbing. And therefore, U at GT is as this expression here. So with that formula in mind, what are the groups that are the most likely to be such that some of their weights and WGT are going to be negative for some T? Yes?
Yes. What T is the length of the spot, right? Yeah. The way this would be, yes.
Yeah. Yeah, that's the length of exposure, yeah.
Longer the length of exposure, the more likely you space.
Yeah, exactly. So the groups for which FG is the lowest, meaning that they adopt the treatment the earliest, then this quantity will be the largest and it enters with a negative sign. So the weight is more likely to be negative. Okay. So the groups that adopt the earliest are the most likely to be such that some of their effects are weighted negatively. And which time periods are going to be such that it's more likely that some effects are weighted negatively at those periods? The latest periods, because when treatment is absorbing with variation in timing, D dot T is going to be increasing over time. Okay. So when you combine these two facts, that means that it's the long run treatment effects of the early adopters that are the most likely to be, that are going to get down weighted first, and that perhaps could eventually get weighted negatively. And so, in fact, if we have always treated groups, then for those groups, this quantity is equal to 1. So it's going to cancel with this one here. And so the weight on the treatment effects of the always treated groups are going to be minus d dot t plus d dot dot. And because, like we just said, d dot t is increasing over time, it's always going to be the case that at the last period, d dot big T has to be larger than d dot dot. So if we have always treated groups, then for sure, some of the weights are going to be negative for the always treated groups at the last period of the panel. Other weights, of course, could be negative, but at least those weights will be negative. So then a first simple recommendation is to actually drop always treated groups from the estimation in binary and staggered designs, which in any case is a recommend, even forgetting about the negative weighting problem or, the weird weighting problem issue, is a recommendation that can be motivated by the fact that if you want to use, then you could want to use other estimation strategies, but if you want to rely on a Diff-in-diff estimation strategy, then to do Diff-in-diff, you need to observe the unit at some pre-treatment period, which you do not in the case of an always treated group, okay? And finally, we can also see from this formula that it could be that all the weights are actually positive, because that's going to happen when the two terms that enter negatively in the weights, those two, are lower than 1 plus d dot dot, the terms that enter positively for every GT. And so, for instance, if the treatment is relatively rare, in the sense that even at the last time periods of the panel, only a small fraction of groups are treated, you have many never treated groups, then this quantity will never be very large, and then it becomes unlikely that this quantity could be larger than the reminder that this minus this thing here, okay? So the idea is that if treatment is relatively rare, that you don't have groups that adopt the treatment very early and you have lots of never treated groups, then two-way fixed effects in a binary staggered design, two-way fixed effects might not estimate the ATT, but at least it will estimate a convex combination of effects. Okay, so the first data question for this chapter, I would like you to use the Wolfer's DID textbook and run the static two-way fixed effect of the divorce rate on state year fixed effects and the UDL treatment, weighting the regression by the state's population to follow what Wolfers and Friedberg had done in their papers, and clustering the standard errors at the state level. So according to this regression, does it seem to be the case that unilateral divorce laws have a positive effect, no effect, or a negative effect on the divorce rate? Yeah. So up, I'm going to run it too. And so we find a small negative coefficient, but that's statistically insignificant. Okay. So then I would like you to execute this Stata command here. Two-way FE weights, div rate, state, year, UDL, type AFTR to say that we are looking at a two-way fixed effects regression. Weight stpop to say that the two-way fixed effect we're looking at is weighted. And then we want to test if the weights are correlated with length of exposure. So do you find that the two-way fixed effect coefficient estimates a convex or almost convex combination of effects? So at least relative to the previous application we saw, the negative weights are much smaller. Up. So yeah, so we estimate, the coefficient estimates a weighted sum of 522 state year specific effects of UDLs, where 490 effects are weighted positively, 32 negatively. And the negative weights sum to this quantity here, less than 3%, which is much smaller than before. So here we could say that we estimate an almost convex combination of effects. Now we test whether the weights are correlated with exposure lengths. And as you can see, yes, they are very strongly so. The correlation between the weights and exposure lengths is actually minus 0.73. And this correlation is highly significant. So so could it be the case then that the two-way fixed effect estimator is biased for the ATT? Yes, if exposure length, if the treatment effects actually vary with exposure length, then this correlation could indeed lead to a bias in the two-way fixed effect estimator. Yes?
I just have like a sort of related question just because I've been triggered on something with the two examples. So here we have we have fewer ATTs. Is there some sort of mechanical relationship between the number of ATTs and the probability of observing negative weights? Or then...
No. Here, you mean with respect to the previous?
Exactly.
Yeah. So the number of cells is gonna be the number of ATTs is going to be the number of cells with a non-zero treatment, up to the fact that it could be that those UHGT residuals are actually exactly zero for a few of those treated cells, but forgetting about that, it's really like just the number of treated cells. So here, it's really just that Well, no, okay. No, that's there is actually thinking about it a bit more. There is actually a bit of a connection. I was going to say, oh, it's just about the sample size, but it's not only about that. So it's sample size, but it's also the proportion of the sample that's treated, and the proportion of the sample that's treated is indeed much lower actually in this application than in the previous one. Which, and related to what I was saying, if you have lots of never treated and nobody gets treated very early, then you're going to have not that many negative weights. So no, indeed, there is actually a connection. Yes?
So now we are checking the correlation between the weights and exposure lengths. But isn't this mechanical according to what we saw before?
Yeah. In some sense, we're just verifying exactly. But then that means that that's mechanical, but that could still lead to a bias because mechanically the weights are going to be correlated with exposure lengths. And then if treatment effects vary with exposure lengths, which they very well might, then we could get a bias. Okay, so far, I've not given you much intuition as to where those negative weights are coming from. And that's because doing so is actually simpler when we start looking at specific designs like we are doing now. So in the context of a binary and staggered design, Goodman-Bacon shows that we have the following decomposition of the two-way fixed effect estimator as a weighted average of 2x2 Diff-in-diffs that compare the outcome evolution of groups G and G prime between periods T and T prime, where the weights V, G, G prime, T, T prime here are weights that are always positive and sum to 1. And we're going to have that those weights are strictly positive if and only if G, the treatment group in the Diff-in-diff, is such that its treatment changes from T to T prime, while G prime, the control group in this Diff-in-diff, is such that its treatment is not changing between T and T prime. So given that the treatment of G is changing from T to T prime, what is the only possible value of G's treatment at T and at T prime? Yeah, exactly. Because you cannot go from treated to untreated. So it's 0, 1. Now, what about G prime? Is there only one possible value of the treatments of G prime, the control group at T and T prime, or are there more than one possible value? 1, 1, and exactly. Okay, G prime, there are two possible values. So a very important takeaway from this decomposition is that in a binary staggered design, the two-way fixed effect estimator leverages two types of Diff-in-diffs. Diff-in-diffs comparing a switching group going from untreated to treated to a never treated group, and Diff-in-diffs comparing a switching group to an always treated group. And the negative weights are going to be coming from the second type of Diff-in-diffs. Okay, and so to illustrate this point, we are going to consider a simple medical example about two patients that had an infection. And actually, the structure of the the structure of the example is actually taken from a similar example in Borosiak and Jaravel 2017. And they have also coined the forbidden comparison terminology that we are going to be using. So the example is as follows. We have two patients, E and L, that are sick. And so they go to see their doctor at the first time period. And then the doctor asks for some lab tests. And the E patient is a bit quicker in doing their lab test, so that at T is equal to 2, the doctor receives the test, see that they have an infection, and gives them antibiotics. And then the L patient is a bit slower, and therefore it's only at T is equal to 3 that the doctor gets the test results back and sees that they have an infection and also gives them antibiotics. So that gives us a setting with 2 groups, E and L, 3 time periods, and we have variation in treatment timing because the E patient is treated at dates 2 and 3, while the L1 is only treated at period 3. So then we have an econometrician that comes by and say, okay, this is a great experiment to measure the effect of antibiotics on fever, let's say. And let's run a 2-way fixed effects regression of the fever of patient G at time T on group fixed effects, time fixed effects, and their treatment status. They do that, and they find So to understand a bit what the 2-way fixed effect estimator is doing, we can use this decomposition here, which in this very simple example with 2 groups and 3 periods, if we compute the decomposition, what it says is that 2-way fixed effect is the simple average of 2 Diff-in-diffs. We compare the fever evolution of the E and L treated patients from period 1 to 2. From 1 to 2, E is a switcher and L is never treated. And then we compare the period 2 to 3 fever evolutions of the L and E patient. And L is a switcher from period 2 to 3, while E is an always treated patient between those 2 dates. So we do that, and then the econometrician finds that the 2-way fixed effect coefficient is actually positive. And so before calling Robert Kennedy and telling him that actually he was right, that modern medicine is wrong and antibiotics do nothing for fever, he scratches his head a little bit and wonders whether there might not be a flaw in their analysis. So is it correct to conclude that antibiotics actually increase fever, or there could be something else that explains the positive estimator?
Yes, our effect on the early treatment.
So there might be a strong effect for the early treated, but then this effect would show up here as well, no? So the effect has to be strong for the early treated? Yeah. And why is this plausible in this very specific example?
Sometimes.
Yeah, exactly. Antibiotics are slow-acting drugs. You know, like they don't start working right away. They may take some time to work. And what might be happening, so graphically, here this graph depicts fever's evolution for the early treated patient and for the late treated one. The solid lines are the actual fever levels of the patients, and the dashed lines are the counterfactual levels. And so you see that the solid lines are always below the dashed lines, meaning that antibiotics always reduce fever. They have a positive effect as expected. But that's an example, exactly as Andrea was saying, where at period 2, the effect is still pretty small because, you know, antibiotics need time to act. But at period 3, now the patient is recovered and they have a really large effect. And the same happens to the late treated patient at period 3. They only start having a small effect of antibiotics. It's only going to be at the next period, which we do not observe, that they will fully recover. And so then our Diff-in-diff estimator is a weighted average of this Diff-in-diff, comparing this decrease to that increase, which is going to be a little bit negative. But then we also compare this small decrease to this much larger decrease, which is actually going to give us a positive Diff-in-diff, which is going to be more positive than the first one was negative. And then we will end up with a positive estimator. Okay, so now let's formalize this a little bit. So the first Diff-in-diff is really our chapter 3 Diff-in-diff. We are comparing a group going from untreated to treated to a group that's untreated at both dates. And so there we know that under no anticipation and parallel trends, it's going to be unbiased for the effect of the treatment for the early treated patient at day 2. The more interesting one is the one that's making the forbidden comparison, and the one that's comparing the switcher to the always treated. So if we look at the outcome evolution of the early treated patient from period 2 to 3, based on their treatment history, the outcome of the early treated patient at period 3 is an outcome with 1 period without treatment, and then 2 periods of treatment, while their outcome at day 2 is their outcome with 1 period without treatment and 1 period of treatment. Then I do my usual trick of adding, subtracting the untreated outcomes, which appear here, and now that's why I get outcomes with treatment minus untreated outcomes, which give me treatment effects. And so I get that the expectation of the outcome evolution of the early treated group is the expected evolution of their outcome without any treatment, plus the change of their treatment effect from period 2 to period 3. Now we do the same exercise, but for the late treated group. The late treated group is untreated at period 2. So at that date, we observe an untreated outcome. And at period 3, it's been treated for 1 period. So we observe their outcome with 2 periods untreated and 1 period treated. I do again my trick of adding, subtracting the untreated outcome I'm missing. And I finally get that their outcome evolution is unbiased for their outcome evolution without treatment plus their treatment effect at period 3. Then I'm trying to analyze what this thing here is unbiased for. Well, this thing here is equal to this minus that. Therefore, the expectation of this thing is equal to this minus this thing. 2 terms are going to cancel, actually, when I take the difference between this and that. What are the terms that are going to cancel out? So what do you mean by the time effects? So the first part, right? Yeah. So those counterfactual outcome evolutions without treatment, under my parallel trends assumption, they're going to be the same for the E and for the L group. So they will cancel out, okay? As assumed in this graph, you see in this graph, I'm assuming that we have parallel trends. Of course, they only cancel out under the parallel trend assumption, but here we are making that assumption. And so finally, then we get that the expectation of this switcher versus always treated Diff-in-diff here is equal to this minus plus this, okay, as stated here. And so finally, I have that the first diff-in-diff entering into the two-way fixed effect estimator is unbiased for this. The second one is unbiased for that. And my two-way fixed effect is just the average, the simple average of the two diffs-in-diffs. Therefore, putting the two equations together, I get that the two-way fixed effect is unbiased for this thing here. And so you see that it's unbiased for a weighted sum of 3 treatment effects: late treated group at period 3, early at 2, early at 3, where the weights a half, 1 minus a half sum to 1, but we have one negative weight. Okay, the effect for the early treated group at period 3 is weighted negatively. So intuitively, the negative weight is coming from the fact that the early treated group is used as a control group while it's actually treated. And because of that, its treatment effect at period 3 gets weighted negatively. Okay, so now coming back to your question earlier as to which type of heterogeneity, is it effect heterogeneity across G, across T, across both that matter for that can lead to a bias in two-way fixed effect estimation? I would like you to find an assumption on the treatment effects such that under that additional assumption, the negative weight in this decomposition here is going to disappear. Yes, so then that means effect homogeneity across G or across T? Across T, yeah, exactly. So actually it's a bad example because homogeneous effects across G would also mean that this effect simplifies with this one, and you would end up with only that effect here. But this is specific to this 3 groups, 2 groups, 3 periods example. The result that holds generally is that if treatment effects are constant over time, meaning that the TE2 and the TE3, the treatment effects of the early treated group at period 2 and at period 3 are the same, then you will have that this is unbiased for the effect of the late group at period 3 plus a half of the effect of the early group at period 2. And this result generalizes to any binary and staggered design, actually. And actually, if you want to, if you're ready to assume that treatment effects are stable over time, and you would like to decompose a two-way fixed effects regression under the parallel trends assumption, but also under the assumption that treatment effects are stable over time, you can use our two-way FE weights Stata command for that purpose. You just need to replace the FE-TR argument by the FES argument. So for instance, here I don't, in this example, it's probably not going to change much. Well, no, actually it is going to change. Ah, bad example. And so you see, as predicted, now we only have non-negative, we only have positive weights. So now, so also the fact that assuming homogeneous effects over time is sufficient to have that two-way fixed effects identifies a convex combination of effects that's specific to the binary and staggered design. In more general designs, that's no longer true. But perhaps more importantly, the assumption of constant effects over time is often implausible because that rules out two things. That rules out the fact that the treatment effect could vary with length of exposure and also with calendar time. Okay, so that's a pretty strong assumption. So now, why is it that so we've understood that the source of the negative weights is the fact that the two-way fixed effect estimator leverages this switcher versus always treated diff-in-diff. But still, is there, so that can lead to a bias if treatment effects are heterogeneous. But is there actually, can this lead to something that would actually be desirable? Is there a reason why actually the two-way fixed effect estimator is leveraging this comparison? Can there be an argument in favor actually of leveraging this type of comparisons? Yes. Efficiency, yeah, exactly. So up to realize that, let's assume that we have parallel trends and that the treatment effect is constant. Then we have that YGT is, of course, the never treated outcome plus DGT times observed outcome minus never treated outcome. You know, one of these definitional equalities relating the observed and the counterfactual outcomes. Under parallel trends, we know that the never treated outcome can be decomposed into a group fixed effect, a time fixed effect, and an error that means zero. And under the constant treatment effect assumption, we have that this is actually just a real number beta. Okay? So what this means is that if we assume parallel trends and constant treatment effects, then YGT, the DGP for YGT, is actually a population version of a two-way fixed effects regression. So what this means is that the two-way fixed effects regression is implicitly assuming constant treatment effects, as reflected by the fact that it puts a single number, beta, that's not indexed by G or T in front of the treatment. Now, with constant treatment effects, this quote-unquote forbidden comparison is not forbidden anymore. Actually, now it's unbiased for the constant treatment effect parameter beta. And at the same time, if we assume that the errors in this population regression here are, if we assume that those errors are homoscedastic and independent and identically distributed across both G and T, which are the assumptions under which OLS estimators are the best linear unbiased estimators of population coefficients by what's called the Gauss-Markov theorem. Then under those assumptions, we can show that the variance of beta at Fe is equal to 3/4 of the variance of the heterogeneity robust Diff-in-diff estimator, where we just use the E versus L comparison from period 1 to 2. Therefore, the reason why two-way fixed effect leverages the forbidden diff-in-diff is just that because implicitly two-way fixed effect is assuming constant effects. Under constant effects, this forbidden diff-in-diff is not forbidden anymore, and using it actually reduces the variance of the estimator. Yes?
Just to go back, so this is a case of variance-bias trade-off in a situation in which just to go back quickly to what you said before, I was wondering, is this result that you quote about homogeneity across time, making this the fixed effect, normal fixed effect regression, okay? Does it hold also for non-absorbing treatment? Maybe this anticipates the...
So good for a binary non-absorbing treatment.
Yeah.
For the FD regression, not for the FE regression. So for the fixed effects regression, it's only true if the treatment is binary and absorbing. But for the FD regression, it still holds if the treatment is not absorbing. So why? I don't know, but that turns out to be the case. Okay, and so now the last thing I want to say about this decomposition of the two-way fixed effect estimator as a weighted average of diffs is that researchers now sometimes use so they've understood that the issue with the negative weights is coming from those quote-unquote bad diffs that use an always treated unit as the control group. And therefore, they compute the Goodman-Bacon decomposition and use the fraction of the weights in that decomposition that's being placed on bad diffs with an always treated as the control group, as a diagnostic tool of whether their two-way fixed effect is robust to heterogeneous effects. Here, I just want to highlight that there is not a one-to-one mapping between the weights in the Goodman decomposition on bad diffs using an always treated as the control group, and the negative weights in our decomposition with Xavier. And so to see that, you can consider first a very simple example, but now I'm just adding a third group N that's untreated from period 1 to 3, okay? So I have my early, my late, and now I have the never treated group. Now, if I run the Goodman-Bacon decomposition in that example, it's going to tell me that I might still have a problem because beta at FE is assigning a weight 1/6 to bad diffs that use and always treated as the control group. If on the same example, I run our decomposition with Xavier, it's telling me no problem, two-way fixed effects is estimating a convex combination of effects. No problem, I don't know, but at least no negative weight. We can reproduce this phenomenon in real data sets, and the general, the thing that we can show generally is that having that your two-way fixed effect leverages diffs comparing a switcher to an always treated is a necessary but not a sufficient condition to have that two-way fixed effect estimates a non-convex combination of effects. And similarly, the weights that the two-way fixed effect places on bad diffs in the Goodman-Bacon decomposition is always going to be an overestimate of the negative weights in our decomposition. And the reason for that is that actually there is not a unique way of decomposing the two-way fixed effect estimator as a weighted average of diffs. And as soon as there are 3 distinct treatment dates, which was not the case in the first example with 2 groups. Then there was only 2 treatment dates, but that's the case in my second example with a never treated group that's adding a third treatment date. As soon as you have 3 distinct treatment dates, you can find another decomposition of the two-way fixed effect estimator than the Goodman-Bacon one. That's going to put less weights on diffs-in-diffs using a group treated at both periods as the control group. Okay, and so the weights computed by in the Goodman-Bacon decomposition are computed by the Bacon decomp Stata and R commands, whose syntax is Bacon decomp outcome treatment comma detail. Okay, so let's resume. So going back to Michele's question briefly, a few things about the the design-based approach, where rather than treating the design as fixed, we treat the design as random, and we assume that we have some knowledge about the treatment assignment process. So AC and Imbens show that if instead of assuming parallel trends and taking a model-based approach, you were to take a design-based approach where you actually assume that treatment date is randomly assigned, then the problem with negative weights goes away. Okay, in that case, you have that the two-way fixed effect estimator estimates a convex combination of treatment effects. And if you're interested, we show it formally only in the context of our simple, 2 groups, 3 periods example. But in that case, it's easy to show, but informative to realize that indeed, if the identity of which group is the early treated group and which group is the late treated one is not fixed, but is actually randomized, which is the difference between an approach conditional on the design and a design-based approach, then the negative weights go away. Now, what are in our opinion, there are a few issues with this type of rationalizations of the two-way fixed effect estimator. The first one is that if group treatment date is randomly assigned, then you actually don't need to run a two-way fixed effects regression. You can just compare, you can just run cross-sectional comparisons of the early and the late treated, and this will unbiasedly estimate the average treatment effect. In fact, it's been shown in a context in a simple diff-in-diff setting with 2 periods. It's been shown by those 2 papers, Friso and Pocock and McKenzie, that a more efficient estimator than in the 2 periods case, a more efficient estimator than the diff-in-diff estimator, if you have that the treated units are chosen randomly in period 2, is actually to run at period 2 a regression of the period 2 outcome on the treatment status, controlling for the period 1 treatment. That this will give you a more efficient estimator than doing diffs-in-diffs, which is essentially regressing y2 minus y1 on the treatment status. So the intuitive reason is that because diff-in-diff is regressing y2 minus y1 on the treatment, it's as if diff-in-diff was implicitly assuming that the coefficient on the regression of y2 on y1 is equal to 1, which may or may not be the case, but when the true coefficient is not 1, it's actually more efficient to regress y2 on the treatment controlling for y1 than regressing y2 minus y1 on the treatment. This type of results extend to designs with variation in timing. Roth and Santana show that they derive with designs with many periods and variation in treatment timing, but where the treatment date is randomly assigned. They derive an efficient estimator of the ATT. And as in the 2 periods case, it's not a diff-in-diff estimator. it's a cross-sectional comparison of the early and late treated, controlling for their baseline outcomes. The second issue that we see with this justification of the two-way fixed effect estimator is that this estimator is rarely used in the context of actual experiments where a researcher randomly assigns the treatment date. It's more being used in the context of natural experiments where the researcher does not have the control on the design of the study. And then in those contexts, assuming that the treatment is as good as random is a very strong assumption, actually, which should be tested very thoroughly. And randomized treatment timing actually has a lot of testable implications because randomized treatment timing means that the treatment adoption date should be independent of all potential outcomes without treatment. But you could have that, let's say that the first group, let's say that you have F-1 periods where nobody is treated, that the first treated group starts receiving the treatment after F-1, then you observe the untreated outcomes for all those time periods, and then you can, for instance, regress the adoption date on all those untreated pre-treatment outcomes to check if indeed the adoption date is unrelated to the pre-treatment. Or conversely, you can run the regression in the opposite direction. You can regress the pre-treatment outcomes on the adoption date to see if you have some correlation. And that's exactly what we're going to be doing in the Wolfers application, where in this regression, so there until 1968, nobody is treated. So all the divorce rates that I observed before 1968 are Y0s, divorce rates without the treatment. And I'm going to check whether those pre-treatment outcomes are correlated with whether a group is an early treated, a late treated, or never treated. And while, so the reference category are the early treated, and while we do find not very much difference between the early and the late treated, the never treated have very different divorce rates prior to treatment, which seems to suggest that the FG variable is not as good as random. Okay, so now second, like we had done in chapter 3, so we've reviewed the static two-way fixed effect estimator. Now we're going to review a dynamic two-way fixed effect estimator where we try to test for pre-trends and we try to estimate effects of different lengths of exposure to the treatment. So the way the event study regression has been generalized to designs where we have variation in treatment timing is as follows. We regress YGT on group fixed effects, time fixed effects, and then we have these relative time indicators that are equal to 1. For instance, this one here is equal to 1 when period T is such that group G has been treated for L periods. And we let L, the relative time, range from some value minus K to a value big L. So one point worth noting is that in practice, when people estimate those regressions, they often do endpoint binning, meaning that for instance, for big L, we replace the equality here by an inequality, meaning that the dummy will be equal to 1 whenever T is such that group G has been treated for at least L periods. And similarly, at minus k, we also replace the equality by an inequality such that the dummy will be equal to 1 whenever group G is at least k periods away from being treated at period t. And this practice of doing endpoint binning is recommended by this paper by Schmiderny and Ziegler, because they show that without endpoint binning, the event study regression is implicitly assuming that after L treatment periods, there is no longer any effect, while with endpoint binning, the regression is assuming that after L treatment periods, the effect is stabilizing. Okay, it's not changing anymore, which is much more plausible actually. Like there is no reason why you would have a treatment effect until L period and suddenly no treatment effect, while assuming that treatment effect stabilized after a certain point seems much more plausible. Okay, so let's estimate this event study regression in the context of the Wolfers application, where we're going to let L is equal to 16, K is equal to 9, and we're going to use endpoint binning, and we're going to weight the regression by population. So then, according to this regression, so remember that in the static regression, there was evidence that actually the ATT was equal to 0.
Mm.
Was this, so do we still find no treatment effects when we use the event study regression? Yeah, exactly. So we find positive effects first and negative effects in the long run, which on average cancel out to 0. But there is evidence of treatment effects. What about pre-trends? Do we find, the pre-trends are very close to 0. Okay, so up the... So those are the event study coefficients. And so we see that initially they're positive and significant. But at some point after, so they are significant all the way till 6-7 years after the treatment. Then they become insignificant. And then 12 years after the treatment, they actually become negative and significant. And when we look at the relative, the pre-trans coefficient, they are pretty small, and none of them is statistically significant. And if we run an F test, that the pre-trends are jointly insignificant, we cannot reject the null. Okay, and the coefficients are shown here. And so you see that here, actually, if we run visually an exercise that, you know, I really recommend you to run to see if linear trends compatible with your first placebo estimator could rationalize your actual estimators. Well, that amounts to taking the here in this case, because the estimates are positive, that amounts to taking the lower bound of the confidence interval on your first placebo, and then you trace the line connecting that to the origin, to the 0 point, and you project that into the pre-treatment period, and you see that at least for the first time periods, it seems that there is really something going on that cannot be just accounted for by differential trends you would have failed to detect.
Oh, sorry. Isn't it strange to have such large confidence interval at the first treatment period and then they become smaller again?
Very strange. So this is for sure something. So, you know, I've not dug into what's really explaining that. This must be something like there is an outlier in terms of the divorce rate at that specific date. That, you know, no longer shows up afterwards. But yeah, and all of the estimators, except for one, is going to be subject to that issue. But usually it's more the opposite that you would expect. Like the weight of the confidence intervals for the remainder of the event study function is very much like you would expect. Broadening over time, because you have fewer and fewer states for which you can estimate the very long run effects. But yeah, like there is really this abnormality here with the observation. So the fact that, you know, if we try to interpret the results a little bit, the fact that the UDLs have a positive effect on the divorce rate, that's pretty much what you would expect. It's easier to divorce, so people are more likely to divorce. Now, the negative long-run effects are a bit more puzzling. And here, I think you can come up with two explanations. One, let's say, you know, substantive explanation, which would be that this increase in divorce correspond to couples that would have divorced anyway, and the reform just makes them divorce sooner than they would have had, and therefore in the long run we see these negative effects that offset the early positive effects. The second possible explanation, you know, the more statistical one, could just be that, you know, we have no pre-trend, but for 8 periods, and those negative effects, they start appearing, you know, a bit after that. So maybe in the very long run, we have differential trends, and those are actually not real treatment effects, but they are just differential trends between the treated and the control. Those are, I think, the two possible explanations. Okay, so we have a similar result for the dynamic two-way fixed effect model as for the static one, which is a result that was actually shown by Sun and Abraham. So they show that under the no anticipation and parallel trends assumption, for positive values of L, namely for the coefficients that are supposed to estimate event study effects, not the pre-trends estimators, then their expectation is actually the sum of two terms. So let's look at the first one. So this one here is pretty similar to the term that we already had for the static model. Namely, that's a weighted sum across groups of effects of L periods of exposure to treatment as intended. Remember that this is supposed to estimate the effect of L periods of exposure. So we would hope that it does indeed estimate the effect of L periods of exposure. And to some extent it does, as reflected in this first term, which is a weighted sum of effects of L periods of exposure with weights that sum to 1. The weights could be negative. So, you know, if those effects of L period of exposure are heterogeneous, maybe that could be a problem, but at least they sum to 1, and therefore, if effects are constant, this term will estimate effects, the effect of L period of exposure. Now we also have this term here, which is different, which is the novelty with respect to the result we had in the static case. This term now is a weighted sum across groups as before, but also across L primes different from L of effects of L prime period of exposure to the treatment. So this means that in my coefficient that's supposed to estimate, let's say in my beta 2 coefficient, that's supposed to estimate the effect of 2 years of exposure to a UDL, actually effects of 1, 3, 4, 5, etc. years of exposure to the treatment are actually also entering into that coefficient. So that means that the coefficient that's supposed to estimate the effect of 2 years of exposure is contaminated by effects of 1, 3, 4, etc. years of exposure. Now we have this result that says that for any L prime different from L, the sum of the contamination weights is equal to 0. So that means that if effects of L prime years of exposure are constant across groups, then the contamination problem disappears. Okay, the contamination term then is equal to 0. So that's not surprising. We kind of know that if treatment effects are constant, this type of two-way fixed effects model work well. We have a confirmation of that here. Even also for the dynamic case, if effects of L and L prime period of exposure are constant across groups, then beta at FEL is unbiased for the effect of L periods of exposure. But if we have heterogeneous effects, then we have the same problem as before, that this term here could not be a very good measure of the effects of L period of exposure if those weights W, L, G, L are not constant across G, and even worse than that, could be negative. And on top of that, we have this contamination phenomenon. So now, so that's a result for the coefficients that are supposed to estimate the event study effects. But that's not the only goal of the two-way of the event study regression. The event study regression is also supposed to give us pre-trends coefficient that we hope to use to test the no anticipation and the parallel trend assumption. Now, another result in the Soon and Abraham paper is that actually those pre-trends estimators can be very misleading if we have heterogeneous treatment effects. What's the reason for that? Well, the reason is that so they decompose. So Soon and Abraham decompose those pre-trends coefficients without making any assumption, okay? Because the goal of those pre-trends coefficients is to test the no anticipation and parallel trend assumption. So to make sure that those coefficients can be used for that purpose, we want to see what they estimate without making any assumption. And so without making any assumption, they show that those pre-trends coefficients estimate the sum of two terms that we're going to call term A and term B. Term A is doing what you would expect. Namely, it's comparing the outcome trends of groups that will get treated in a few periods and groups that will not get treated in a few periods, which is what you would want to do if you want to test no anticipation and parallel trends. Okay, so term A is doing what we would expect this type of pre-trends coefficients should do. Term B, on the other hand, is the exact equivalent of this, with different weights, meaning that the pre-trained coefficients are also contaminated by actual treatment effects. So that means that the pre-trained coefficients are estimating the sum of differential trends before treatment of the treated and of the early and late treated, or the never treated, but also treatment effects. And because of that, you could have situations where no anticipation and parallel trends assumptions are satisfied, implying that term A that I was referring to is equal to 0. But the pre-trend coefficients are still not equal to 0 because of the contamination terms, because of the fact that those pre-trend coefficients are contaminated by actual treatment effects. So that means that you could look at your pre-trend estimator and you could reject the no anticipation and parallel trend assumption because the coefficient is significantly different from 0. But actually, it's not because the non-zero coefficient is not due to a violation of no anticipation and parallel trends. It's just due to the fact that you have contamination. And conversely, you could have DGPs where the parallel trends and no anticipation assumptions are violated, meaning that this term A I was describing is non-zero, but it's, for whatever reason, it's exactly offset by term B coming from the contamination by treatment effects. And therefore, your pre-trend coefficient is equal to 0. So you wrongly conclude that you have no anticipation, you have parallel trends, while in reality, you don't. Okay. So that's a very important part, I think, of the result in Sun and Abraham, which is to show that in the presence of heterogeneous treatment effects, the pre-trend estimators from event study regressions can be very misleading. Okay, so Sun has actually a event study weights data command that computes the weights attached to two-way fixed effect event study regressions. And the syntax is event study weights, and then you put in all the relative time indicators that you would have in your actual event study regression. And then you need to specify a group and a time indicator. And then you need to have like yeah, so you need to have like a cohort variable that indicates when it is that a given group was treated for the first time, and the relative time variable is length of exposure to the treatment. Alternatively, another command that you can use to decompose event study regressions is, again, the two-way FE weights command. The syntax is going to be the same as before, except that you need to account for the fact that now, unlike the static regression, the event study one does not have a single treatment variable. It has many treatment variables, all the relative time since treatment that need to be imputed into an option that's called other treatments, because this command allows to decompose two-way fixed effects regressions with more than one treatment variable. So for instance, you would put, if you want to decompose the coefficient on the first event study effect, you need to put the relative time indicator for being treated for one period as the main treatment variable, and then all the other relative time indicators into the other treatments option. And if you also have relative time indicators before treatment adoption, then you need to put those into the controls option as if they were control variables. Okay, and so, yeah, maybe I can go over a few to understand a little bit where the contamination problem is coming from. We can go over a few simple numerical examples. But essentially, the idea is always going to be that the two-way fixed effect event study regression implicitly makes strong assumptions that treatment effects are constant across groups. If you do endpoint binning, that treatment effects are not changing anymore after a certain point in time, etc. And then, under those assumptions, by Gauss-Markov theorem, OLS is just a machine to try to form efficient estimators of regression coefficients under the assumption that the errors are uncorrelated. So it's going to try to find all the possible diffs-in-diffs it can form, even though that those diffs-in-diffs might sound ex post a bit crazy to us, but they are not crazy under the strong assumptions that we implicitly make when we estimate those regressions, and they lead to efficiency gains with respect to just using the more natural diffs-in-diffs that ex ante or we would have seemed natural to use. So let me start with one example. So for instance, we consider a case with two groups. T is equal to 4. We have an early treated group that gets treated at T is equal to 2, and a late treated one at T is equal to 3. And we're going to estimate the event study regression with L is equal to 2. So we want to separately estimate the effect of 1 and 2 periods of exposure. We use endpoint binning such that when a group reaches 3 or more periods, it's still the same dummy as for 2 periods. And we have no pre-trends. So in that case, it's possible to show that beta at FE1 is a simple average of those two diffs-in-diffs. This one here is the natural, like the one that you would think of using naturally. It's comparing the early and late treated group from period 1 to 2, namely when the E group becomes treated and L is untreated. That one, you would never have thought of using it ex ante. It's comparing the outcome evolution of the late and early treated group from period 2 to 4. So at period 2, the early group has been treated for 1 period. At period 4, it has been treated for 3 periods. And the late group, at period 2, it's untreated. And at period 4, it's been treated for 2 periods. So why on earth would that actually help us estimate the effect of being exposed to treatment for 1 period? Well, that's because you can show that because the treatment group in this comparison, the late group, is untreated at 2 and treated for 2 periods at 4. This is estimating the effect of the late group at period 2 minus the control group. Well, the control group has been treated for 3 periods at period 4 and for 1 period at period 1. So we subtract the effect of 3 treatment periods minus the effect of 1 treatment period for that group. But now, because we do endpoint binning, we're implicitly assuming that 3 treatment periods has the same effect as 2 treatment periods, and therefore this is equivalent to an effect of 2 treatment periods. And because we are implicitly assuming that all groups have the same effect of being treated for 2 periods, this difference cancel out. And then you're left with this. And this, crazy looking Diff-in-diff estimator is actually an unbiased estimator of the effect of being treated for 1 period under all the implicit assumptions that are being made by the event study regression. And you can actually show that with almost kinetic and IID errors, adding the second Diff-in-diff is indeed reducing the variance of the estimator. So it's always the same the same story. So I'm not going to go over the second example because it's really the same, but there is this one here that took us a long time to figure out that for the pre-trends estimators, why is it that pre-trends are getting contaminated? Well, we have an example where we have 3 groups, 3 periods, an early treated, a late treated, and a never treated. And then you can show that the pre-trend estimator is leveraging, so you have the early treated becomes treated at period 2. So for that one, you cannot compute a pre-trend estimator. It's treated too early. So the only group for which you can compute a natural pre-trend estimator is the late one. And you can do that by comparing the outcome evolution of the late treated to that of the never treated from period 1 to 2. Okay, and Diff-in-diff is, so the event study is doing that. But then it's also adding this weird looking term where those are Diff-in-diffs comparing the early and never treated from period 1 to 2. So when the early becomes treated, and we do the same thing, but for the late treated from period 2 to 3, when the late is becoming treated. And the idea is that, okay, so those are going to be estimating effects of one period of exposure to treatment if we do not assume homogeneous effects. So that's where the contamination problem is going to come from. That's where you see that the pre-trend is actually contaminated by a weighted sum of effects with weight that sum to 0, like the Abraham and Soon result was saying. And the reason why, so of course, if effects are homogeneous, the contamination bias disappears. And then you can show that adding this term here actually reduces a lot the variance of the estimator. Okay. So let's do one. Let's conclude by applying the results we just saw to decompose the first event study estimator in the UDL example. So the syntax is a bit more complicated for the event study regression. So I can show it to you right away. So I want to decompose the coefficient on this treatment variable, the indicator for having been treated for one period. But I want to take into account the fact that actually I have other treatment variables in the regression as indicated here. And I also have pre-trend estimators which play the role of control variables in the regression. And I run this. And so now you see even the output of the command is becoming really, really complicated to read. And that's because, don't blame me. I did not invent two-way fixed effect event study regressions, but that's up. So here, like in this case, this result is saying this is estimating a double summation across L and G of fx. And L actually here takes 16 different values. And so the command is going to give you essentially, as succinct as possible description of 16 sets of weights. And so the first set of weights are the weights on the effects that you would expect, namely the effects of one period of exposure. We are decomposing the coefficient on the coefficient for having been treated for one period. So we hope that it's going to estimate effects of one period of exposure. And it does. The first term is a weighted sum of 27 effects of one period of exposure, where all the effects are positive. Okay, so at least no negative weights in this sum. Now we see that the coefficient is contaminated by effects of 2 years of exposure to a UTL. Fortunately, with weights that sum to 0, okay, as expected. Fortunately, the contamination weights are not very large. So we see that there is a bit of contamination taking place, but the weights placed in front of effects of 2 years of exposure are not very large. Same thing, we also have that the effect of 1 year of exposure, the coefficient on 1 year of exposure is contaminated by effects of 3 years of exposure, 4 years, 5 years, etc., all the way to 16 years of exposure. But each time, the contamination weights are relatively small. And finally, we have a bit of a correlation between the weights and the year variable. Again, as always, a negative correlation. So the more time passes, the less weight we put on effects, which means, so the correlation is, but the correlation is not super statistically significant. So overall, in spite of those, like potentially very alarming results, in this specific example, at least, all the weights on this summation are positive. And yes, we have contamination, but so fortunately, I did not even remember that. So it's probably something that, no. No. So that's due to the endpoint being. But yeah, fortunately, when you sum across all the L primes, the value of the contamination weights, they are pretty small. So it seems that the issues we just discussed might not be that severe actually in this specific application. Okay, so tomorrow we're going to start, we will discuss potential heterogeneity robust Diff-in-diff estimators, but I think we're going to stop here for today because, it's almost time and we've covered a lot of ground. Is there any question before we stop?
I will just start with a question myself. So we showed that the weights for the first part were not negative in this case, but I guess it's because we focused on the first dummy in the first event after the treatment. If we go later on, probably we'll start having some negative weights. So because we showed that the later we go, the more negative weights we have. So I would expect that maybe.
But we don't really have a plus one expression for the weight. It's extrapolating intuition from the static case to the velocity case, which might not be completely unreasonable, but let's try. Yes. So, I chose a bit randomly, and I think that's pretty correct. No, you see?
Okay, interesting. Yeah.
I don't know about let's see if we have more contamination. Yeah, it's maybe a bit more. Yeah, there seems to be a bit more contamination actually. If you have some all those contamination weights, I think it would be a bit larger than that.
And I also have another question regarding the binning. So I know that then we will use other estimators, but if we focus on the 2fx effect, would be reasonable not to bin, to include everything. So after 16, keep on going on until possible, and then maybe not to show the later period because in the later coefficients, because probably we are binning because we don't have enough sample size towards the end. So maybe it's better to saturate the model and then just focus. Exactly.
Have more weeks,
closer. Yeah.
Yes, but that's not solve the negative weight contamination. No. Even what's called. So what you describe it called the fully dynamic
exactly.
Where we go to the maximum L and to the minimum K.
Yeah. So
you still have a similar decomposition results as and so the two groups, the sequential example I gave had endpoint binning, but actually I skipped because exactly to make sure that people get the point that actually even without endpoint binning, we have a numerical example where even without endpoint binning, the regression that ends up using weird.
Sure. It probably remains.
I realize that exactly. Good. So yeah, so see you tomorrow then.